So welcome to our databases course. This is the fourth course in the class, and if you have taken all three, you have learned a bunch. There's a lot in this class. If you're 2 weeks into this class and you didn't take the prerequisite courses and you're like, what are these people talking about? Well, that's what those other courses are. Don't say, oh, why don't you give me a basic intro to Python? And the answer is we did that. That's what courses 1, 2, and 3 were. You'll notice that in courses 3 and 4 that we're going more slowly through the book. The material is more complex. The lectures take longer to sort of develop. In this, we're going to learn object-oriented programming, we're going to learn structured query language, and we're going to do a little bit of visualization. And in a way, structured query language is the biggest part of this class. We're going to learn about database design, and this is really so that ultimately, if you need to use databases as part of a Python program, you're competent in databases. And so this is more about database than it is about Python. We're going to learn about, like I said, database design, one-to-one relationships, foreign keys, joins, select, delete, update. I love SQL, structured query language, and I think you probably will too. Most beginning students prefer SQL in a way to Python. Because SQL is a fundamentally different pattern for writing software. In Python, you have learned that you got to be very explicit, like do this, then do that, and keep track of this other thing, and then check back in that other thing, and like add a thing to this other thing, and then print these stuff out and sort them. And you're like, do it. And it's a bunch of really simple kind of things that you construct orders and patterns and loops, and that's what you're good at by now. In SQL, you kind of do it all in one statement. You're like, do this, where that happens, pull this other stuff in, blah, 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 and then magically you get exactly what you want. You kind of write single statement programs that are themselves internally interesting and complex, kind of like regular expressions. But regular expressions are not essential, but SQL in lots of job situations is essential. So I think that you should look forward to learning SQL. It's a fun language. It's different, so get ready for that. And then what we do at the very end is we do a little bit, bring it all together and do some analysis and visualization and scraping, which is really sort of a preview for the fifth course or the capstone, where we're just going to do analysis, visualization, and scraping. So welcome to course 4. I hope you enjoy it. So we started this entire course printing hello world. And I just said, quote, hello world, quote. And out comes hello world. And it'd be nice if that was super simple. And, you know, in 1970, it was simple because there was pretty much one character set. Even in 1970, when I started, we didn't even have lowercase characters. We just had uppercase characters. And I tell you, we were happy when we just had uppercase characters. You kids these days with your lowercase characters and numbers and slashes and stuff. So the problem that computers have is they have to come up with a way. I mean, computers don't understand letters, actually. What computers understand is numbers. And so we had to come up with a mapping between letters and numbers. And so we came up with a mapping. And there's been many mappings historically. The one that sort of is the most common mapping of the 1980s is this mapping called ASCII, the American Standard Code for Information Interchange. And it says basically this number equals this letter. So for example, the number for hello world, for capital H, the number is 72. Somebody just decided that the capital H was going to be 72. Lowercase e, the number is 101. And new line is 10. So if you were really and truly going to look at what was going on inside the computer, it's storing these as numbers. But the problem is there are 128 of these, which means that you can't put every character into a 0 through 128. And so in the early days, we just kind of dealt with whatever characters were possible. Like I said, when I started, you could only do uppercase. You couldn't even do lowercase. And so there is this function, as long as you're dealing with simple values, that you can say, hey, what is the actual value for the letter H? And it's called ord. which stands for ordinal. What's the ordinal? What is the number corresponding to H? And that's 72. What's the number corresponding to lowercase e? It's 101. And what's the number corresponding to new line? And that is a 10. Remember, new line is a single character. This also kind of explains why the lowercase letters are all greater than the uppercase letters, because they're ordinal. For ASCII, now there's so many character sets, but just for the default old school 128 characters that we could represent with ASCII, the uppercase letters had a lower ordinal than lowercase letters. So high is less than Z, 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 all lowercase. And that's because all lowercase letters are less, all uppercase letters are less than all lowercase letters. Actually, this could be A. That's what I should have said there. Okay, so don't worry about that. Just know that they are all numbers. And in the early days, life was simple. We would store every character in a byte of memory, otherwise known as 8 bits of memory. It's the same thing when you say I have a many gigabyte USB stick. That's a 16 gigabyte USB stick. That means there are 16 billion bytes of memory on there, which means we could put 16 million characters on here in the old days. Okay? So the problem is in the old days, we just had so few characters that we could put one character in a byte. And so the ORD function tells us the numeric value of a simple ASCII character. And so, like I said, if you take a look at this, the E is 101, and the H, capital H, is 72, and then the new line, which is here at the line feed, which is 10. Now we could represent these in hexadecimal, which is base 16, or octal, which is base 8, or actual binary, which is what's really going on, which is nothing but zeros and ones. But these are just, this is the binary for 10, 0, 0, 0, 1, 0, 1, 0. And so these three are just alternate versions of these numbers. The numbers go up to 127. And if you look at the binary, you can see in this, this is actually 7 bits of binary. You can see that's all ones. So it starts at all zeros, goes on to all ones. And so it's like zeros and ones are what the computers always do. And if you go all the way back to the hardware, the little wires and stuff, the wires are taking zeros and ones. So this is what we did. In the 60s and 70s, we just said whatever we're capable of squeezing in, we're just totally happy. We're not going to have anything tricky. And like I said, halfway, early in my undergraduate career, I started to see lowercase letters. I'm like, oh, that's really beautiful. Lowercase letters. Now, the real world is nothing like this. There are all kinds of characters, and they had to come up with a scheme by which we could map these characters. And for a while, there were a whole bunch of incompatible ways to represent characters other than these ASCII, also known as Latin character sets, also known as Arabic character sets. These other character sets just completely invented their own way of representing, and so you had these situations where Japanese computers pretty much couldn't talk to American computers or European computers at all. The Japanese computers just had their own way of representing characters, and the American computers had their own way of representing characters, and they just couldn't talk. But they invented this thing called Unicode. And so Unicode is this universal code for hundreds of millions of different characters and hundreds of different character sets, so that instead of saying, oh, sorry, you don't fit with your language from some South Sea island, it's okay. We've got space in Unicode for that. And so Unicode has lots and lots of characters, not 128, lots and lots of characters. And so there was a time, like I said, in the 70s and the 80s, where everyone had something different, and even like in the early 2000s, as the internet, what happened was as the internet came out, it became an important issue to have a way to exchange data. And so we had to kind of say, oh, well, it's not sufficient for Japanese computers to talk to Japanese computers and American computers to talk to American computers. We want Japanese and American computers to exchange data. So they built these character sets. And so there is Unicode, which is sort of this abstraction of all the different possible characters. And there are different ways of representing them inside of computers. And so there's a couple of simple things that you might think are good ideas that turn out to be not such good ideas, although they're used. So the first thing we did is these UTF-16, UTF-32, and UTF-8 are basically ways of representing a larger set of characters. Now the gigantic one is 32 bits, which is 4 bytes. It's 4 times as much data for a single character. And so that's quite a lot of data. So you're dividing the number of characters by 4. So if this is 16 gigabytes, it can only handle 4 billion characters or something, divided by 4, right? 4 bytes per character. And so that's not so efficient. And then there's a compromiser, like you have 2 bytes, but then you have to pick. This can do all the characters. This can do sort of lots of character sets. But turns out that even though you might instinctively think that like UTF-32 is better than UTF-16 and UTF-8 is the worst, it turns out that UTF-8 is the best. So UTF-8 basically says it's either going to be 1, 2, 3, or 4 characters. And there's little marks that tell it when to go from 1 to 4. The nice thing about it is that UTF overlaps with ASCII, right? And so if the only characters you're putting in are the original ASCII or Latin 1 character set, then UTF-8 and ASCII are literally the same thing. And then use a special character that's not part of ASCII to indicate flipping from 1 byte characters to 2 byte characters or 3 byte characters or 4 byte. So it's a variable length. And so you can automatically detect, you can just be reading through a string and say, whoa, I just saw this weird marker character, I must be in UTF-8. And then if I'm in UTF-8, then I can sort of expand this and represent all those character sets and all those characters in those character sets. And so what happened was they went through all these things, and as you can kind of see from this graph doesn't really say much other than the fact that UTF-8 is awesome and getting awesomer, and every other way of representing data is becoming less awesome, right? And this is 2012, so that's a long time ago. So this is like UTF-8 rocks, and that's really because as soon as these ideas came out, it was really clear that UTF-8 is the best practice for encoding data moving between systems. And that's why we're talking about this right now. Finally, with this network, we're doing sockets, we're moving data between systems. So your American computer might be talking to a computer in Japan, and you got to know what character set's coming out, right? And you might be getting Japanese characters, even though everything I've shown you is non-Japanese characters or Asian characters or whatever, right? So UTF-8 turns out to be the best practice. If you're moving a file between two systems, or if you're moving network data between 2 systems, the world recommends UTF-8, okay? So if you think about your computer, inside your computer, the strings that are inside your Python, like x equals hello world, we don't really care what their syntax is. And if there's a file, usually the Python running on the computer and the file have the same character set. They might be UTF-8 inside Python, it might be UTF-8 inside, but we don't care. You open a file, and that's why we didn't have to talk about this when we were opening files. Even though you might someday encounter a file that's different than your normal character set, it's rare. Okay, so files are inside the computer, strings are inside the computer, but network connections are not inside the computer. And when we get to databases, we're going to see they're not inside the computer either. And so this is also something that's changed from Python 2 to Python 3. It was actually a big deal, a big thing. And most people think it's great. I actually think it's great. Some people are grumpy about it, but I think those people just are people that fear change. So there were 2 kinds of strings in Python. There were a normal old string and a Unicode string. And so you could see that Python 2 would be able to make a string constant, and that's type string, and it would make a Unicode constant by prefixing U before the quote, and that's a separate kind of thing. And then you had to convert back and forth between Unicode and strings. What we've done in Python 3 is this is a regular string and this is a Unicode string, but you'll notice they're both strings. So it means that inside of the world of Python, if we're pulling stuff in, you might have to convert it, but inside Python, everything is Unicode. You don't have to worry about it. Every string is kind of the same, whether it has Asian characters or Latin characters or Spanish characters or French characters, it's just fine. So this simplifies this. But then there's certain things that we're going to have to be responsible for. So the one kind of string that that we sort of haven't used yet but becomes important, and it's present in both Python 2 and Python 3. Remember how I said in the old days a character and a byte were the same thing. And so there's always been a thing like a byte string. And you do this by prefixing the B. And that says this is a string of bytes that mean this character. And if you look at the byte string in Python 2 and then you look at a regular string in Python 2, they're both type string. The bytes are the same as string and the Unicode is different. So these two are the same in Python 2. And these two are different in Python 2. I'm not doing a very good picture of that. So the byte string and the regular string are the same, and the regular string and the Unicode string are different. So what happened is in Python 3, the regular string and the Unicode string are the same, and now the byte string and the regular string are different. Okay? So bytes turns out to be raw, unencoded. That might be UTF-8, might be UTF-16, it might be ASCII. We don't know what it is. We don't know what its encoding is. So it turns out that this is the thing we have to manage when we're dealing with data from the outside. So in Python 3, all the strings internally are Unicode. Not UTF-8, not UTF-16, not UTF-32. And if you just open a file, it pretty much usually works. If you talk to a network now, we have to understand. Now the key thing is we have to decode this stuff. We have to realize what is the character set of the stuff we're pulling in. Now the beauty is because 99% or maybe 100% of the stuff you're ever going to run across just uses UTF-8. It turns out to be relatively simple. So there's this little decode operation. So if you look at this code right here, when we talk to an external resource, we get a byte array back. Like the socket gives us an array of bytes, which are characters, but they need to be decoded so we know if it could be UTF-8, UTF-16, or ASCII. So there is this function that's part of byte arrays. So data.decode says figure this thing out. And the nice thing is you can tell it what character set it is, but by default it assumes UTF-8 or ASCII dynamically, because ASCII and UTF-8 are upwards compatible with one another. So if it's like old data, you're probably getting ASCII. If it's newer data, you're probably getting UTF-8. And literally, it's a law of diminishing returns. Like it's very rare that you get anything other than those two. So you almost never have to tell it what it is, right? So you just say decode it, look at it. It might be ASCII, might be UTF-8, but whatever it is, by the time it's done with that, it's a string. It's all Unicode inside of this. So this is bytes, and this is Unicode. So decode goes from bytes to Unicode. And you also can see when we're looking at the sending of the data, we're going to turn it into bytes. So encode takes this string and makes it into bytes. So this is going to be bytes that are properly encoded in UTF-8. Again, you could have put a thing here, UTF-8, but it just assumes UTF-8. And this is all ASCII, so it actually doesn't do anything. But that's okay. And then we're sending the bytes out the command. So we have to send the stuff out. Then we receive it, we decode it. When we send it, we encode it. Out in this real world is where the UTF-8 is. Here we just have Unicode. And so before we do the send and before we receive, we have to encode and decode this stuff so that it works out and works out correctly. And so you can look at the documentation for both the encode and the decode. Decode is a method in the bytes class, and it says, you can see that the encoding, we're telling it, you can say it's not UTF-8, ASCII and UTF-8 are in the same thing. The default is UTF-8, which is probably all you're ever going to use. And the same thing is true. Strings can be encoded using UTF-8 into a byte array, and then we send that byte array out to the outside world. And it sounds more complex than it is. So after all that, think of it this way. On the way out, we have an internal string. Before we send it, we have to encode it, and then we send it. Getting stuff back, we receive it. It comes back as bytes. We happen to know it's UTF-8, or we're letting it automatically detect UTF-8, and decode it, and now we have a string. And now internally inside of Python, we can write files. We can do all kinds of stuff in and out of this stuff, and it sort of works all together. It's just that this is UTF-8 question mark, question mark. This is the outside world. And so you kind of have to look at your program and say, okay, when am I talking to the outside world? Well, in this case, it's when I'm talking to a socket, right? I'm talking to a socket, so I have to know enough to encode and decode as I go in and out of the socket. So it looks kind of weird when you all of a sudden start seeing these encodes and decodes, but they actually make sense. They're sort of like this barrier between this outside world and our inside world, so that inside our data is all completely consistent, and we can mix strings from various sources without regard to the character set of those strings. So now what we're going to do is we're going to rewrite that program. It's a short program. but we're going to make it even shorter.
Hello, and welcome to my video that shows how to get started and install Python on Microsoft Windows. Okay, so it's not too hard. We're going to both install Python 3 and we're going to install text editor. And so I'm just going to go into Google and I'm going to say install Python 3. And my top link is downloading Python. And there is my link for downloading Python 3.5.2. This version of my class uses Python 3. I have an earlier class that you may have seen that uses Python 2, but in this class we're going to do this. Now it might take you a while to download this. I've actually already downloaded it. Now the other thing we need is a programmer text editor. And you can really use any programmer text editor. We've used Notepad Plus in the past. We've used JEdit in the past. I like Atom, Atom.io, Tom.io, mostly because it works the same on Windows and Mac and Linux. But you can really use any text editor that you like. Just don't use Word or text edit that comes with the operating system. You need a programming editor that doesn't mess with weird characters or weird lines or strange formats. You must have a real programmer editor. So I've already downloaded this as well. And so I won't waste the time waiting to download it, but let's go ahead and do the installation. So these things ended up in my downloads file. So I'll go to downloads and I'll start installing Python 3.5.2. Now it's going to ask me some things. Add Python 3.5 to the path. Yeah, that's a good idea. Install the launcher for all users. I'm going to add that. Maybe you will, maybe you won't do that. It's going to tell me where it's going to install it. Install now. Of course, it's going to ask me for permission to do these things. And now it's running through the installation. Okay, so there we go. You could maybe click on this online tutorial and documentation. But we're just going to close this. And I'm going to start and run the Windows command line. Now, you may have all kinds of fancy ways to run Python, but I like running the command line, command. I like running the command line because it's after a while, it's important to know what folder things are being run in. And so here's this command line, and I should be able to type Python here. And so now I'm in Python 3.2, and this is the chevron prompt here is the Python interpreter, where it's asking for Python commands, and I can say print hello world. Of course, this is what we tend to print all the time. I can make a mistake. I can say blah, blah, blah. Right? And it'll complain to me. Now to get out of this, I can either type Control-Z or quit. In this case, I'm going to type Control-Z, and I'm back to the prompt. A couple of things. I can do a dir to see what folders and files I have, and that is like my desktop. And then the cd command tells me where I'm at in the folder. That means I'm in the users directory, Dr. Chuck. Okay, so I have now installed Python. I ran the Python interpreter to verify it. I said print hello world. Okay, and so now what I'm going to do is I'm going to actually install Atom. And I already had this downloaded, so let's go ahead and install Atom on my computer. Okay, so Atom is now installed and it's kind of telling us what to do. I'm going to actually just close all these windows, close this window, close everything, and I'm going to create a file. I'm going to say print, in this case, let's see if I can make this bigger. I can make it bigger. So I'm going to type print hello from a file. Okay, and I'm going to save this. I'm going to say File, Save As, and what I'm going to do is I'm going to go to my desktop, and I'm going to make a folder on the desktop. I'm going to call this folder PY4E. So I now have a folder on the desktop. Move this here. I'll move this here. Oops. And I'm going to go into PY4E, and then I'm going to name this file first.py. And you'll notice that when I save this, it syntax highlighted it. That's one of the nice things about a programmer editor. Okay, and so it says, oh, it's got a suffix of .py. So therefore, it knows that it's supposed to look pretty with Python and make this one color, make this another color. The other thing that you'll notice is that I now have a folder called PY4E. And if I'm in this command line, let me just start that up again. I'll show you how to start the command line again. Command. Now, if I do a dir, I see the folders that I'm in. And one of the folders that you can see here is the desktop folder. So I'm going to say cd desktop. And then I'm going to type the dir command to see what folders are in the desktop. These folders are the same as these folders. These things are kind of virtual folders. PY4E is PY4E. Now I can type cd, which stands for change directory, PY4E. And I can do a dir, and now you see first.py. And that's the same as if I'm diving into this folder. Here's this file, first.py. Windows hides the suffix, which is somewhat annoying and frustrating, but that suffix is there, that file is there. And so for me, one of the things you got to figure out in Windows is how to make sure that you are in the same folder, users, Dr. Chuck, desktop, Pi4E, and that's the name of this file, and here as well. And now I'm going to run this program. I'm going to type Python first.py. And you see that it ran the Python code. Okay? Another way you can do this is you can type first.py. And that's because this file association has happened in Windows. This doesn't work in Macintosh. This only works in Windows. That all files with .py are expected to be Python, and it knows the Python interpreter where to run it. Okay? And so I've got Python 3.0 installed, and that gets me started. And so I hope that this little introduction about getting things started and writing your first Python program has been helpful to you.
Hello, and I'd like to talk to you about how to use the snipping tool to do a screen capture. There are other ways to do this, but the easiest way is the built-in screen tool. And I'm doing this on Windows 8. The snipping tool exists on earlier versions of Windows as well. And so the gestures and the UI might look a little different, but it's about the same. You find the snipping tool. So I'm going to hit the Windows icon, and I'm going to type the SN, and it brings up the snipping tool. And so here I go, and it's giving me this option to say snipping tool. And I'd like to say I'm going to do a new window snip. And now it's kind of graying out the screen and following me around with this little red line. And I click on this, and it has made a copy of that window. Now snipping tool is just the snipping tool. That window still exists, but this is now, oh, I didn't want to do that. This is now just a drawing tool. That's so so here you are. We could save this, but the other thing you can do, and this is in the more recent snipping tools, is you can make changes. So let's say, for example, you didn't want to show your name, and your name was in this path, and so I will just go and scribble my name out, like with this little scribbling tool. Pretty sweet, huh? So there I scribbled my name out. I just happened to have my name in it, so I didn't want to put it in. So now I'm going to do File, Save As, and of course find somewhere. I'm going to put this on my desktop, and I'm going to call it notepad.png. Now you don't have to put the suffix of .png or JPEG, but it's good if you're moving files between systems to put these suffixes on. Windows would know this was a PNG file, but .png is a way to nicely tell other systems when you're moving it around that it's a PNG file, or if you send it as an email or whatever. So I save it. I'm saving it on my desktop, and there we go. So it's hiding the .png, but I can look to make sure the PNG is really there, and so there it is. It's a .png, and so there's a file, and away we go. Okay. So there's the snipping tool. If I close this window and I click on Notepad, you will see that it's got the little scribbling thing. Thank you for that. Okay, so there you go. That's how to do a real simple snipping tool. In this video, we're going to actually download and install Python 3 from python.org on a Macintosh. If your Macintosh for years has wonderfully come with Python 2. So if I type Python ---- version, then if I type that, I see that I've got Python 2.0. What we want to do is, in addition, install Python 3. One of these days, Macintosh might upgrade their distributed version of Python 3. But there's so many things inside Mac that depend on Python 2. I'm going to expect that it will always be named Python 3, which is what we're going to call it in a second. So here I am at the python.org downloads, and I'm going to download Python 3. You click here, and I've actually got it sitting here in downloads already because I always do that. And so, I'm going to install this. There is the installer. I'm going to say continue, continue, continue. Of course I agree. I read all that really fast, and now I'm going to install it. Okay. So now that means if I run a terminal, so this of course is start run terminal. So Python 2 is still there, but Python 3 is also now there. So we should have Python 3 installed. So we installed Python 3.6, and so there we go. And that's all it takes to install Python 3 on the Macintosh. So let's write our first little Python program. I'm going to, I like Atom, and so I've got this Atom editor. It's atom.io. Right here, atom.io. Download and install the Atom editor. I like it because Atom works the same on both Windows, Mac, and Linux, and it has syntax highlighting, and so I really like things like that. So I'm going to make myself a simple Python program. Hello world, like we always do. Now you'll notice that it's not syntax highlighting yet, but I'm going to do a file, save, oopsie daisy, file, save as. And I'm going to go into my desktop, and I'm going to make a folder called py4e. I'm just going to call this hello.py. Oh, crud. Got to rename it. Rename it. I ended up with 2 dots. Hello.py. There we are. And so now I'm here, and I'm in my home folder. I can go in my desktop, and I can go into that new folder I made, Python for Everybody, and I can see the files. Now, there are ways to run this, and I really want you to learn the terminal so that you really know what you're doing. And so here we are in the folder that has the Python, and then all we do to run it is we say Python 3 hello.py, and there we go. And of course, this is Python 3 because I'm using parentheses there. So instead of double quotes. But Python 2 is still there. And of course, if you just run Python hello.py, it'll be a syntax error or not. Must be they added something. Yeah, because Python is still version 2, but apparently they allowed print in the latest version of Python 2. So away we go. Okay, so again, thanks for watching. I hope this was helpful to you to get Python 3 installed on your Macintosh. Hello and welcome to the podcast on taking screenshots on the Macintosh. Nicely, Macintosh has a very simple tool built in. We go into Macintosh hard drives, we go to applications, and then we search down for preview, preview right here. So preview, and I'll close this now. So we've got preview. Preview is the application that was originally built to view PDFs on the Macintosh, but it also has a whole series of screen capture capabilities. And I like to keep preview in my dock all the time, so I come down here on the preview icon, and it's already in my dock. If I said remove from dock, and then I would say keep in dock. It was already there. As soon as I start preview, I always keep it in the dock. I put all the things I need to use all the time in the dock. And so let's take a screenshot. I'll just sort of start a JEdit program. And I'll say take me as a screenshot. Whatever. Doesn't matter. Just this is the window that I want to take a picture of. This window right here. So I go to preview and I say file. This is in the most logical place. You can either grab a rectangular selection, in which you'll be allowed to draw with your cursor, or a window, or the whole screen when timed. 90% of the time, what you really want to do is take a window. You say grab window. It tells you, you can go over different windows. I can click here. I can click there. I can click there. And I just want to capture this window. So click. I go like that. Now here's a little weird. This is now an image. Okay, and so you can't click on this stuff. Okay, that's that. So what you need to do, I'm going to close the original real window now. This is my JEdit. I'm going to Command Q to get rid of JEdit, and I do not want to save that file. So now I'm in preview. See, I'm in preview here, and so I've got this as an image. Now the one thing it does is it always saves it to your desktop, which gets to be sort of painful after a while. It gives them these long names called snapshot that has the date, and it stores it in this format called TIFF. So I prefer to switch it to a non-Apple format, so I want to do a save as, and I'm going to save this as a JPEG, and I'll give it a better name called first image, and it'll be a JPEG, and I'm going to store it right on my desktop. So now here we have first image, okay, and I can click on that and take a look at it. I'll close this, click on it. Interestingly, it just comes back up in preview. So that's pretty much it. This would be the file that you would upload if your job was to do this. I'll show you a couple other tricks that I like to make my images a little bit better. Preview has a simple tool for cropping. And the way you crop something is you draw a rectangle here on the image, and then you say Tools, Crop. And now I've gotten rid of all the rest of that image except that which I want, and I'll say save this as and I want to save it as JPEG tiny. I'll save it as tiny. And so I now have two images. I got that first image and I got this tiny image, and there it is. I'll use Command W to quickly close it. I really like Apple W to quickly close it. And so the one thing is you just, after a while, these snapshots fill up on your desk, and so just keep cleaning them off. And if you were uploading to hand in a screenshot or whatever, this would be the file that you upload. So that's pretty much all there is. Use the preview command to take screenshots with the grab, and typically it's grab window. Okay? Thanks.
So welcome to chapter on object-oriented programming. I have been using terminology all along about object-oriented programming. I say object, like beautiful soup returns the soup object, and then I call the find method within the soup object and I get back a list, blah, blah, blah. And I didn't want to teach you object-oriented programming too early in the class, because until you need it, you sort of don't need it. So I've been using these words without defining them. And so guess what? Now is the time that we're going to define these words. I'm not going to ask you
to write objects. I'm not going to ask you to build your programs using object-oriented techniques. You will eventually love OO and object-oriented, and you'll be good at it. But in this class and in this lecture, I just want you to have a few words that you absolutely 100% understand. And I'm going to give you some sample code, but not so you can write that code, but to help inform your understanding of the concepts. Because object-oriented is something that I think you have to come back to a couple of times. You can't just like see it and go, got it. Like a lot of things in programming, until you really need them, it's hard to fully understand them. But we got to start and learn somewhere and then come back again. So the word objects has been in, like I said, a lot of the words I've said. We've been reading documentation. They say the word object. What is object? Well, it says here the list data type has some more methods. Here are the ones that list of the list objects, and that means the objects of type list. And list data type has methods. Methods are these things that are functions built into objects. And I've said these words before, and now I want us, by the end of this lecture, to know these quite well. So as we're moving, our next stuff is we're going to move into databases. And database is a connection object, and a cursor object, and an object, and a method, and call a method. Again, I just want you to know these words. So let's go back to the beginning and start with programs that we started with. And here was our first program that handled input, processing, and output. You can draw a boundary around this program, right? And there's kind of like the inside stuff and the outside world, okay? And to the outside world, this program does something. And frankly, if this is the outside world, we do not have to keep track of the detail of this. Like, we've got this program, we installed it on our computer, we're confused about floors, and we're in Europe, and we're saying, yeah, I'm on floor 0. What would be the equivalent US floor? Thank heaven I have this application, right? And so there is this notion of kind of like inside and outside, where we hide the detail. Like, programmers have to worry about this detail, the programmer that wrote it, but a lot of people don't. So this is kind of hiding, abstraction. There's a lot of words that we use to basically say, don't worry about what goes on inside. And so in actuality, that program had several objects in it. The string object, there's an integer object. And so what happens is these objects also sort of are like containers of functionality, of containers of awesomeness. And these objects sort of work together. And the program itself kind of orchestrates these objects, one or more objects working together. And the best way to think about an object is kind of like a program but smaller. It's a little thing that we can draw a boundary around and say, oh, there's some code and data in there. There's logic, there's data, and we do stuff with it. And the idea is you take this big problem and break it into a series of problems like small Lego blocks, and then build these things back up to build your program. And like I said, we have been using objects the whole time: strings, integers, dictionaries, lists, floating points, etc. And so if you think of a program, it's going to have different kind of objects that are in it, and these objects are going to work together to take the input of the program and produce the output of the program. And like I said, we've been doing this all along. But one of the things about objects is that each one contains some code and some data, and you can send stuff back and forth between objects. You can make new objects. You can do stuff with objects. But one of the things is like, okay, if you're in the object, you just say, oh, this is what this object does, and I'm not going to worry too much around the world in which I'm embedded. And the same thing is true about the outside world. We're going to use this object, and we're not going to look on the inside of it. So from outside looking in, you ignore the detail. From inside looking out, you ignore the outer detail. And so it's a way to draw a nice bright line and say, you worry about this, and we'll worry about that. And it's a separation of concerns. And so some terms that we're going to be using are class, object, method, and attribute. And so a class is a shape of an object. It's a template. In the little example, it's like the cookie cutter. And then the object is like the cookie. And so you can say, I would make a bunch of objects. So the string is a class. We have as many strings. We have a string called X, and we could have a string called Y, and a string called Z, and X could have something different than Y and Z, etc. But the class is string. And then methods are like uppercase, string.uppercase. That's a method. That's a capability. And attributes are data that's part of a class as well. And so, and objects. And so we'll get to these. So a class is defining the general characteristics of a thing, like what fields it has, what properties it has, it's a blueprint for making things, right? class dog is all dogs, but then you would make each dog then would be an object. The concept of dog is like a class, but when you see a dog and you grab the dog, that's an object. An instance is another word for object. And so this is where we have dog, and then we have many actual dogs, or cookie cutter, and then many actual cookies, okay? And so the object or instance is the word we give to the real things, not the shape of the things, but the real things. Method is a part of the defined in a class. It's also part of the object, and that is things like string.upper, string.starts-with, string.find. Those are all methods in the string class, but they also are part of every string object. In some forms of object-oriented, sort of the simpler, prettier, pure, they would call it a message, meaning that here's this object and you're going to send it a message to cause it to do something. You would kind of poke it with this message. But another way to say is it's got code in it, and we call a function inside the object. And they're kind of equivalent, but sort of just one to some people seems prettier than the other. For me, I tend to think of it as like code. We're calling a function that lives in the object. So, like I said, we've been playing with these objects all along. We have, a string object. And when we print this type thing out, now we're going to understand a little bit more. And that basically says that X is an object of type class, the class string, right? So that's what the kind of thing. This is an instance of the string class. This is an instance of the float class. This is an instance of the integer class. We make a list. Say, what is it? Well, this is an instance of the list class. What is this? Type Z is a dictionary, and that's a class. Now, so these are all the classes. Those are the templates. You can have many strings, many instances. An object, this is the object. This is an object. This is an object. We can also ask, based on these things, what are the capabilities? And these that we've seen before are the methods. In our X, we've got stuff like upper. That's one of the methods. In Y, which is our list, we can append, we can pop, we can remove, we can sort. So there's all kind of methods in lists, and in dictionaries, we've got things like items, values, get. Remember get, how we use it in counting? Well, get is a method that's part of all dictionary objects. And so we've been playing with these things all along. It's just that now we want to make this terminology nice and precise. So up next, we're going to talk about how you would build your own class in Python. And it's not so much that I want you to build a bunch of classes, but really to help as you look at how we define them, to kind of think as how a string class might be defined or how you use a string class. So now we're going to take a look at building a bit of Python and building a class in Python. Not again so much as because I want you to write a bunch of code, but instead I want you to imagine as you're using classes that someone had to write this code. And so we're not going to make you write a bunch of classes, but we're expecting you to be increasingly good at using classes that are built into Python or come from libraries that you might import. And so here's some code. So class is kind of like a function. There's a new keyword called class, and then there is the name of the class party animal, and so that's the name of the class, a colon, and then an indented block, and so it's got sort of a block of text that makes up the class. And as I mentioned, every class has some data associated with the class and some code associated with the class. And so here in this class, we just have some variables, x equals 0. That's an attribute of all party animals will have a variable named x in them, and there's a little function. And so this is now a method. So it has a bit of code. It's a method. And then when this is done, it doesn't actually run any code. But what happens then is we have a template called party animal. And this syntax here that basically says, make me a party animal, it's the same as saying x equals list parenthesis. That says, mint me a new list. There is a template for a list here. And then give it to me, give me that empty list back in the variable x. So that's what's happening here. Mint me a new party animal based on the template that's up here. And then once that empty or fresh party animal is done, then give it to me back in the variable an. And so this then is that object. So that is a party animal object. Using the party animal template makes a party animal object, which ends up in the variable an, or the party animal, an instance of the party animal class. And then we make a call by taking the name of the object, dot is the operator, and then the method within it. So that basically calls this code. Okay? And then it calls it again, calls it again, calls it again. You can put parameters here, and you'll notice that this party has no parameters and this one has one parameter. And what basically you can think of this as, it's kind of like saying go into party animal, call the party function within that, and then pass as the first parameter this variable. So that you can almost think of this syntax as this is like a contraction for this, which says go in, find this party animal, and then pass an. An, the variable, comes in as self. Now, you don't have to name this self, but you can name it self, and nearly everyone who writes Python object-oriented tends to call this self. And self says self.x equals self.x plus 1. Well, that's kind of like saying an.x equals an.x plus 1, because we're calling it in the context of an. And so when we see more than one instance, we will see how this all works. And so this is basically the object. We have the definition, we have the minting, the templating, the making of the cookie, and then we have the use of that object. And so if we trace through the code that's going to happen here, there is nothing, there is just a template, and then we mint this, and then in the minting it runs through this and defines these things, and then x ends up with the variable value 0, and then this whole object, this whole box is the object because it has a variable, an attribute x, and a bit of code called party, and then we take this, that it gets returned, and then it comes back as an. And so an sort of points at this particular object when this line of code is done. So make the thing from the template and then assign it to an, so an points to this. Then what happens is we hit this, and so that goes up and calls this party, except that an is self as an alias to an. So temporarily, self is also pointing to this. And then it says self.x equals self.x plus 1. So that pulls the 0 out of here, adds 1 to it, becomes 1, stores it back in, which makes this be a 1. And then it also has a print, so far self.x, and that prints out this print. Then it returns, goes to the next line. The next line goes up to here, passes in an again, so self also points to this object that now has a 1 in it. And it comes in, self.x equals self.x plus 1, so it pulls this variable out, adds 1, this becomes 2, it goes back into self.x, so that becomes 2. Then we print this out, so far 2, then we finish, go down to the next line, comes back up, runs it again, this becomes 3, and then it prints out, so far self.x is 3. And so that's the logic of it. It's just kind of so far it's like a clever way to hide or embed a function inside this template. Now, in reality, they would have multiple methods and multiple bits of data, and so it's more complex than this. But for now, this sort of just gets us started to understand the syntax of the class, what we call the moment of construction. This is the moment of construction right here where it's being constructed, and these are the invoking of the methods within the object. Now, like we've shown, the type and the dir tell us what kind of things these are. And the dir tells us what the methods available are. If we take a look at the thing we just created, so class party animal, and we make a new party animal and assign it into an, and we say, hey, what is the type of an and what is the methods that are available in an, it will basically say an is of type class main.partyAnimal. That's what it is. And so it says that's the kind of thing that this is. The template from which we created an is this template right here. And so it knows that and remembers that. And then dir says, what are the things in there? And you see a bunch of things with underscores. Those are internal. But eventually you see party, which is this method. And you see x, which is this attribute. And so dir is like looking or inspecting inside here and say, well, what things are in here? And you see party and you see x. And so dir, when dir is looking into a string, it's doing the same kind of thing. It's like, oh, what little functions live inside of strings? And that's what we do. You know, we have like strip, split, strip, upper, right? Those are the functions that are like in the code that someone wrote a long time ago to make strings and define strings. And again, it works the same for classes that we define and then create instance of and then use. So up next, we're going to look into a little more detail of this notion of constructing and destructing multiple instances of objects. So now we're going to talk about how objects are built and then thrown away. And this is, again, something that's been happening all along. Most of the time we build variables, you say x equals hello world, that sort of makes an object. And then when the program ends, all the variables get thrown away. Sometimes you can be a little more explicit. We have terms that we use to describe this. We call it constructor or construction, of taking the template, which is like a pattern, and then building it. And then that's construction, and then throwing that away and making the memory available for the rest of the program is the moment of destruction. You know, if you say x equals hello world, you've constructed a string and put it into x. If you say x equals 12, you know, you construct a 12 and put that in x, but you also have thrown away the hello world that was in there before. So destructors kind of happen as we reuse variables or as the program ends. So, and as our objects get a little more complex, the primary purpose of the constructor is set up initial values. And this has to do with the fact that outside the object, you just say, make me one of these things, make me a party animal. But inside party animal, it may need some data, and it may need that data to be set to 0 or something, who knows what. It's initial, but it's something that the moment of construction, outside we say, hey, construct me one of these things, and inside we say, oh, hang on, I've got all these little things I got to get right before this object's actually going to work. Because think of objects as like small programs that we're like sending stuff into, almost like little mini applications that we got an API to talk to, except it's really tiny and it's just really part of our program. So the way this works is the constructor and destructor are specially named methods. And so in this case, we make party animal, and so far this part's the same and this part's the same, but we have an underscore init, and passing in self, which is that passes the instance of this particular one once it's constructed. And all we're going to do is print out that I'm constructed. This is the same, and then underscore del is when that thing is thrown away. And so it's going to say I'm destructed and print out the current value of x for that particular instance. So it comes through here. It has a template. So it's the same as the one we've been doing. And now we're going to construct. So we're saying construct me a party animal. You know the template because I told it to you. We're not passing any data into the constructor. Eventually that will come in as additional parameters. Make me one of these things, and then it's sitting here. It's got a little x in it. It's got this underscore init. It's got this party, and it's got an underscore del. That's an object now, and that comes into an. And now we're going to call the party method, and that runs and adds 1 to self. But at the moment of construction, it prints out this construction message. Then at the moment of calling that method, it says so far 1, and then so far 2. Now this is kind of like inside this an, there's an x that's got 1, and then it changes to 2. We out here have no responsibility for this x. The person who built this had made the x, and we just get one for free because it's part of the template. Now, we're going to destruct this by saying, oh, an equals 42. So the way to think about this is an sort of points to this object, and then we say an equals 42. It makes a new 42, and then an points to that, and this is thrown away, and then this is thrown away. And the moment, that's the destructor moment. And so in this line of code, it's going to say, before we throw this away, you've got a registered destructor, call the destructor. So in this line of code, you see the end, the last thing that comes out of this object is I am being destructed and my last value of x was 2. And so then this is thrown away and can be reused, and then 42 is there, and then we print out an contains 42. So the end of the program, this doesn't have a destructor because we don't have a print statement inside of an integer class because we didn't make the integer class, but all things are destructed at the end too. And so if there was a thing, you could see a destructed message after the end of the program, because that's where all the objects eventually are thrown away and put back so that the memory is available for other things. So the constructor is the moment we ask to say, make me one of these things, and the destructor is whether if you reassign the variable or if the program ends, then all the destructors get called. So the constructor is a special block of statements that are called at the moment of object creation. Now we're going to talk about what happens when you have more than one instance. We've made a template and then we've stamped out effectively one cookie and put it in a variable, but now we're going to do more than one. And the key thing to start to realize is that the template is sort of replicated multiple times, and then each one can have a different color frosting on it. And so there are instances of cookies, and they can have things like frosting color that changes. And so each of the instances has their own set of variables. So it's not a class variable, it's an instance variable. And so here we have our party animal. And so it's going to be pretty much the same as what we've been doing. We have a variable X, we have an internal variable named name, and again, this is on the inside. We aren't worried about this out here in the main program, but they're defining for themselves a structure. And we're going to have a constructor parameter. So the self is the instance itself, which points to the under construction instance, and then Z is this parameter. So we're going to take the Z that comes in on the parameter and stick it into the name inside the object, and then print out that we've been constructed, and on and on. So that's what's going on. That's how the constructor works. We don't have a destructor in this particular one. And so as this code runs, this code sort of creates the template, then says make me a party animal, and I want that to be with the Sally as the parameter, and so Sally ends up in here, and then S, our variable S, points at that object. And then we're going to call, by the way, and X starts out at 0 through the constructor, because the constructor sets up X to be 0 and then sets self.name to be whatever this parameter is. And then we call S.party, and then party runs and adds 1 to X, so that becomes 1, and then comes back. And now we say, let's make another one. And so let's construct this one with Jim. So it makes another template, which means it has an X and a name and some code in it. And the X ends up 0, and the name ends up Jim. And then we take this thing and we assign it into the variable J. So basically J points at this, and we say J.party. And so this is where, when we say J.party, it comes up here, and in this case, J, self is an alias for J, so it's functioning self.x equals self.x plus 1. That means this one is going to go to 1, because this is the J one, and that's what self means for now. So temporarily, self points at J, and then it prints out self.name party count equals, away we go, and that says this will be Jim, and that'll be 1. And now we've still got S pointing to this, and so we can call S.party, and this time this is an alias to S, so self points to this guy now, and so self.x equals self.x plus 1 means this X is going to get incremented. So these are two X's, two names, but they're sort of independently stored in each of those objects. And so these are two independent instances. The key here is instances, and that's because we minted or caused to be constructed two party animals and then had them in separate variables. And so simultaneously, each one of them has all the internal structure that they need. Now, this isn't a very useful example. Think of this as, you got a bunch of strings, and one in X, and one in line, and one in Z, and one in this, and one in name and email, and they're all strings with data inside of them. And so the variable names kind of are pointing at the objects that have all the data within them. So up next, we're going to talk about another method of defining the capabilities of objects called inheritance. So multiple instances are we have one template, and we make multiple variables out of that template, and they all kind of have the same shape because we're starting from the same template. Inheritance is a different concept. Inheritance is we're going to make more than one template, and we're going to have a second template that's related to a first template. We call the first one a parent template and the second one a child. And the idea is it's like we're going to make a class, a template that's everything that this class has plus. We can either add capabilities or extend the capabilities of the parent. And so the idea is this is just a form of store and reuse. And again, don't get too worried about when you're going to use this. I really am trying to define for you the notion of inheritance rather than teach you how to write inheritance in object orientation. That will come in time, perhaps years from now, when you will actually use this skill. But it does tell you something about how things are related. And if you say, oh, this extends that, then you say, oh, okay, that just means that all the features of the thing that's being extended come in. Another term for this is subclasses. A subclass is a more specialized version of a parent class. Sometimes you have a parent class and a couple of different subclasses. The parent class might be animal, and then you might have a dog, a cat, and a bird, right? And so there are things that animals have, or mammals might have animal, mammal, dog, cat, right? And so that might be a hierarchy of classes. Now, don't get too stuck on that. It's just a form of storing and reusing functionality so that you don't have to repeat yourself. And it's not like the more inheritance you use, the better your programs are. Sometimes that's not true at all. But we programmers just hate repeating ourselves. And so if we can do it once and then reuse it, we like that. And so that's really what inheritance is there for. So here's a bit of code. This first part is unchanged. So we have a class called party animal. It's got two variables, name and x, that are attributes of that. We have a constructor, and the whole idea of the constructor is just to grab that name parameter, and then we have the party, which just adds 1 and prints out the current party count. And that's fine. We've done that before. Now we have a new class. So now we say class football fan, and in parentheses here, we have the name of a different class. So what we're saying is party animal, football fan is everything that party animal is plus whatever we define down here. Okay, so this is like an extension. It's as if all this was pulled in, and then this is addition. Okay, so a football fan has an X instance variable, a name instance variable, and a points instance variable, and has a constructor, a party method, and a touchdown method. And so all of these things, all this stuff is like stuck right there. It's like it came in by us saying, the way I read this in English is class football fan extends party animal, which means it includes everything party animal includes, plus this extension stuff that we're going to add, right? All the capabilities of party animal and more. And so if we're going to use these, I mean, the fact that we've extended it doesn't mean that this one goes away. And so we can still construct a party animal with the name of Sally and call the party method in that, and that does what it does. And then we can make a new object using the football fan template, and give it name, and that football fan actually calls, there is no constructor here, and so it's actually calling this constructor, the one from party animal, because party animal is included in football fan, and it's setting the name and x to 0 and the name to nothing, and then points to 0 also happens. So all three variables are present in this J object, and then we call the party method, which is really here, runs the code. But then we also have now a touchdown method that can run this code. Okay, and so you can see that this football fan has every capability that the party animal has, plus one more capability that we've added. And so that's the basic idea of extension. You know, x is 0, the name is Sally, it runs s party, so x becomes 1, right? That's just a little object with a name s, and away we go. If, on the other hand, we look at this next bit of line of code, right here, we end up with a football fan, and a football fan inside of it has an X, it has a name, and it has points. And at moment of constructor, X is 0, name is Jim, and points is 0. Then we call the party method, and the party method changes the X to X plus 1, so that becomes a 1. The touchdown method, I add 7 to the point, so that becomes 7, and then it calls the party method. And so it's calling within itself the party method. And so that calls that code, and that causes this to turn into 2. So even within this method, you can call other methods. And so this J object has everything that the S object had, and then some. So, again, I just want you to get these words. Classes have attributes and methods. Attribute is data. Method is a function that's part of a class. An object or an instance is what we construct from the template. So class is the cookie cutter and object is the cookie. And a constructor is a bit of code that runs at the moment of object creation. And inheritance is the ability to define a new class and add the existing capabilities of an existing class to make that class. And so that's kind of the definitions. It's you look at it and you say, why did they invent this? And that's probably the right logic to have right now, because you haven't written programs that are complex enough to require object orientation in terms of the code that you write. But we've actually been using object orientation all along, because it's a way to group functionality. Something as complex as beautiful soup, or our SQLite connections. Those things are actually complex data and code, and we don't have to worry about that. And so the benefit to us right now is it simplifies our programs to make use of objects that others create. Some time from now, when you become a more sophisticated programmer, you're like, oh, I got to solve a problem, and I'm going to start creating a bunch of objects to solve those problems.
So now we're going to move into talking about databases. And it may seem a little strange to be talking about databases in a programming language, but we are using this programming language for doing data analysis. And so it turns out that it's quite often necessary when you're pulling data, especially data you're pulling over a network where you might be rate limited, or you want to store the data in a database. You have a process that reads the data and puts it in a database, and then you can analyze it out of the database. And it makes some of your processes go really fast. It allows you to change your analysis and not lock your analysis into the retrieval of the information. So it speeds up your overall workflow, but you have to learn a bunch of stuff so that you can put the information into your database. Now the first task that you have is to install your database browser. There's a couple of different ways to read and write these files. We're going to use Python to read and write the files, but we want a way to read and write the files directly. And so this is a code that you can download for the Mac, for Windows, for Linux. And there's also a Chrome plugin that you can get for SQLite that you can do everything that we're doing in the class. And so I don't really care how you achieve the things you're going to achieve in the class, because we're going to grade you not so much about how you use things, but instead we're going to look at the databases that you produce. Okay, so stop now, download this, install it. It should be simple, should be easy. Check with the forums if we have some problems. So relational databases are a whole subfield of computer science, and it might be best to talk about what life was like before relational databases. You use relational databases thousands of times a day without even knowing it. If you imagine something like a learning management system where there's hundreds of thousands of users and terabytes or petabytes of data, and you log in and within a half a second it shows you what you're supposed to see. You can't read petabyte of data in a half a second. You just can't. And in the early days, we used to have data that was small and computers that didn't have a lot of storage in them. And so we tended to use tapes. And we would put the data like on a magnetic tape, and we would sort the data. We would have the old bank balances on one tape. We would have the transactions, and then we would apply read one balance, check to see if that transaction, if it changed, then we'd store the balance. And then you would have like last night's bank balances and tonight's bank balances. And then the next day you would put this over here and read the old bank balances and make changes. And this is how day after day in the 60s and the 70s we would update data. And if you look at old computer videos, you'll see these little spinning things. Well, those are tape drives. And that's where most of the real data was stored. And it was, but as computers got faster, as they got more memory, and as we started to store data more in the memory of computers and on the disk drives, whole different ways. So you didn't have to read to get through the account that starts with a letter S. You didn't have to read through all the data from A through S just to get to my account that starts with S. And then it'd be like, oh, wait a sec, we have a disk drive that we can skip all the way and skip back and skip over here. And so the problem became how to make use of this random access medium in which we can store data in a way that's efficient and fast and clever. So just because you could randomly access the data didn't mean it was fast. You still had all the data to look at, and if you just looked at it sequentially. So relational databases were this applying cleverness to how we would use random access data storage, mostly disk drives that spun. And it really sort of emerged in the 60s and the 70s, and whole companies were formed like Oracle. Oracle exists because smart people figured this problem out before other smart people did. And so they got to form a company, and Oracle's the leading database vendor on the planet, and much of its revenue comes from its database product and things built on top of its database. But literally, before 1960, the concept of database really wasn't an idea. It was something that happened as storage and what we wanted to do with computers. So this is where if you had to really read a tape to log into a computer, it might take 4 hours to log in, which would be unacceptable in this modern day and age. As I mentioned, the database is sort of this technology that emerged, and it emerged from a lot of theoretical analysis. And the underlying foundations of database have to do with some really powerful mathematics. And so this powerful mathematics still is present in some of the terminology that some people use to describe databases. And so there's really kind of two parallel terminologies that you will encounter. You'll pick a book up and you'll kind of be able to read it and say, oh, this is using the highfalutin, hoity-toity language, which is the more math-oriented. So in the more math-oriented, we use the words relation, tuple, and attribute. That's kind of the fancy way of speaking about it. But sort of we programmers who just do our thing, we would call it a table, a row, and a column. Now, table and row and column is kind of the wrong way to think about it if you're trying to understand the true underlying amazing mathematics. The underlying mathematics is, don't worry about the underlying mathematics. Just be aware as you're reading. Don't be surprised when people lapse into this more fancy nomenclature. So the idea is that you model data at a connection point. Rather than like, here's data and we're starting here and we're reading through it, the idea is if you model everything as a connection, like who a person is a connection between this, that, and the other thing. And so this notion of modeling stuff at a connection is the underlying math that makes databases fast. But when we programmers think about it, we kind of think about it as rows and columns. And so here's just a screenshot of a spreadsheet that I made. Along the bottom, you see the names of the various subsheets, tracks, albums, artists, genres, and titles. And those are like the database tables. And then each table, if you select it, has a row and a column. And so it's got these columns. This has 3 columns in it, and it has a bunch of rows. The other thing, when you're doing stuff in a spreadsheet, you just kind of come up with a data model, a schema, a strategy, so that you know that the first column is always the title, second column is a rating, because if you didn't label it, it would make no sense. So we often do something where the first row of a spreadsheet is kind of metadata about the columns, right? Now, the spreadsheet doesn't exactly know that you're doing it, even though some of the things you do, like sometimes it sorts and says, oh, check this tick box to say the first row is title, so don't sort it. So when you sort stuff, you only sort like the bottom part of it, right? And so it sort of knows that the title, but in a database, this becomes what we call the schema. All these titles, and we have rules, like this have to be integer numbers. This has to be an integer number. This has to be string, no more than 128 characters. So we make strong contracts about the content that sort of at some level feels very similar to what we're doing when we're writing these titles, but in reality, as you'll see, is far more complex and far more intricate. Now, if you've ever tried to do something like we're going to do with this database, and that is categorize your music collection, you find that a spreadsheet is a really hard way to categorize your music collection because of so much repeated data, and we'll figure that out in databases. So the idea that they came up with in the 60s and the 70s is there was a way to represent data on a disk. And it could be randomly accessed, and there was pointers that pointed to something else, and whatever. And in the early days, they figured out how to technically solve fast access to lots of data by sorting, hopping in various ways, indexing, doing clever things. And the early ways that we programmed these databases is we sort of revealed to us application programmers the low-level capabilities of read this thing, then jump to this other thing, then read this other thing, then jump to the other thing, read this thing, jump to this thing, which made our lives really difficult. And so we had to write really sophisticated programs, but when we did, they could function very rapidly. And so what happened over time is instead of our code talking directly to the files or the databases, instead a layer started to build up that we called the database application or database
database. I'm not doing a very good job drawing there, right? So here's our database, and it has lots of complexity in it. And originally we would sort of just talk straight to that complexity, but after a while we would have a database application, and then our application, our code, would talk to the database application, and the database would know all the magic stuff. And it was what we call in computer science an abstraction, which means that our job, this is us, and our job was easier because of the complexity could all be hidden here. And so the question becomes, then how do we talk to this really powerful piece of software that we call a database? What is living here? What is the way we communicate? Sometimes we would call this an API, Application Program Interface. So this is our application. This is actually another application. The database itself is an application. And so we have to have an interface so that our application can talk to the other application. And just like in the previous lectures, this is like a service. It's taking care of it. And ultimately, let me change the color here. It's getting kind of messy. We can sort of think of this thing right here, both the data and the software that understands the shape of the data, as just a service in a service-oriented architecture. So once again, what we have to do is define, to use the service-oriented architecture, the cut point. What is the cut point between our application and this magic stuff? And this is Oracle, right? So it's lots and lots of money. And it's amazing. It's just really good software, right? Oracle's really good. Microsoft's really good. So what happened was we decided to create a standard at this point. The industry did. Folks got together with the National Institute of Standards and Technology, NIST, and they agreed on a language that was the API between an application and a database system. And the name of that thing they came up with was SQL, or the Structured Query Language. Okay? And so that means that, wow, I've made such a mess of this, I have to start over again and draw another picture, right? So that means that over here you could have Oracle, over here you could have Microsoft, and here you could have App 1, and here you could have App 2. And App 1 could talk to Oracle, or it could talk to MySQL, or App 2 could talk to Oracle, or App 2 could talk to MySQL. And so because they use the same communication between Oracle and MySQL, it means that you can write an app that's portable between different databases. And it turns out that this SQL is a beautiful language. It's just a gorgeous language. The reason I don't teach SQL as the very first programming language is you would be ruined. If you learned SQL, you would never want to program in any other language. I think it's the most beautiful language that I've ever encountered. It's beautiful because of its simplicity and its expressiveness and its power, but then it's a very beautiful and elegant language. The problem with SQL is it depends on the data being pretty. It's a great way to write code about really gorgeous data. So part of what we're going to do is learn how to make the data look really good and then write really cool stuff. Python, on the other hand, is a little rougher on the edges, but it just has no problem dealing with unstructured data or data that's imperfect or whatever, and you can just keep writing more Python, and eventually you're like, oh man, I thought it wasn't as complex as this, so I got to add a little bit of if statement here and add another if statement there and do another thing. So Python handles unstructured, rough data much better than databases, and that's why Python plus SQL is such a powerful thing. Python cleans up the data. SQL is a great way to store and retrieve data. So what SQL does is it has 4 basic functions. We call it CRUD: create, read, update, and delete. Update is missing here. CRUD. So that's a database term, is CRUD: create, read, update, and delete. So up next, we're going to talk about how you as the application developer are going to interact both in large projects and in small projects. Small projects are going to be the more typical thing that we use in this class. So that's what we're going to talk about in a bit, and how you use software to interact with databases. So now we want to talk about how we place the database and the database software in relative to the other aspects of the programming environment that we're going to build. And we're going to talk both about large projects and small projects. And a large project would be sort of a website, like maybe you build a website to track comic books or something, and you store all the data in a database. And so in a large project, and and we're not going to do it in this so much in this class, but I figure it's time, now that we're learning about databases, to sort of give you a sense of how they're used in these online systems. And maybe in a future course, you'll see how they're used in, learn how to do this in large projects. But there are generally sort of two roles. One is the person who writes the application and produces the user interface for the application and for the website. And then there's the other that actually sort of monitors and adjusts the database. And that person is the database administrator. Often in a large project, you will get some advice as an application developer from a database administrator. And the idea is the database tuning and monitoring is a somewhat specialized job. And so in a professional environment like the open source learning management system that I work on named Sakai, in production, I don't get as a developer, so that's who I am. This is me. I'm a developer. I write cool code. I make really neat widgets for the end user, and this is the end user in a web browser talking to my cool thing, and I add a little button and stuff like that. And I write code that actually talks to the database server, which is both code plus the data storage itself. And I write code that talks SQL to the database server and gets data back and then formats it for the end user. And that's what developers do. They are the ones that create application software. The database administrator, generally we don't let the developer talk to the database, the production database, directly, because we're afraid the developer will break it. And that's probably because there's been a lot of experience where developers broke it. So we have a special person called the database administrator. And they're the ones that are allowed to talk to the database. Now, because the database is both storage and software, it can take SQL queries from many different sources, both the application or database tools. And so the database administrator has like a direct way to talk to the database and get data back. And so if something's going wrong, like it's gotten really large, what's going on? So the database administrator will start running commands straight to the database, whereas the developer generally has no access to the real database. Eventually we can write a new version of the application software. And so that's kind of the split between the roles between developer and database administrator in large projects. And the database administrator does helps with the design and implementation, and often a database administrator is shared across a number of software projects. But that's not exactly what we're going to do, right? So it'd be nice, maybe you have a job, maybe you do have a job that there's a database administrator and it'll kind of look like that. But right now, during this class, we've met the database administrator and the application developer, and they're both you, okay? They're both you, or me, right? And so what's going to happen now is you get to do both roles. And later, if you have somebody to help you with it, you might turn more into the developer side or more into the database administrator side. That's perfectly fine. So we still have a database system, right? And that's got both the logic, the software that makes the database smart, and the data itself. And we talk to it. And the program we're going to use initially right now is we're going to study the DBA way of doing business. You're going to write SQL. You're going to talk to this little piece of software that's going to submit stuff directly. And so you are going to act as a database administrator. We're going to create tables, put data in them, and we're just going to type stuff in to this application called SQLite Browser. There are others of these applications that are like database administrator applications. Much later, we are going to start writing Python programs. And in those programs, we're going to talk to the same database files using SQL. And we're not going to write programs that have a web interface. That would be like Twitter or comicbookregistry.com or whatever. We're going to have various sources of input, sometimes files, sometimes network. And we're going to write programs that read this stuff and clean it up. Often there's a cleaning step. And then we are going to write the data into a database. And so we're going to grow this data, fill it up. And then we'll sort of be done with this phase of acquiring data, and all our data will be sitting in a database. Then we will write another Python program to read this data and maybe make a pretty file. And even later in the class, we will be visualizing that or sending it to various other places. You might send it to R to do statistical analysis, or Excel to do some simple analysis or visualization, or we'll use JavaScript to make pretty pictures and spinning things and whatever. So the basic pattern here is it's the same. We're going to have sort of apps and then we're going to have DBA, but they're both U. So the thing we're going to focus on first is right here. The database we're going to use is a thing called SQLite, and the software we're going to use is what I told you to install right at the beginning a while ago. Hopefully you've done that, SQLite browser, because otherwise you can't talk to the database unless you have something equivalent to this, and they do exist. But the basic pattern is read data, clean it up, stick it in the database in a sensible and organized way, and then write other applications to make sense of it and analyze the data. And that's what we're going to be doing coming up. So when we build this data, I mentioned the word schema, right? That we come up with a contract for exactly the way the data is supposed to look. And with this contract, the database software can make the best use of itself, right? It can make good use of the disk drive. It can make good use of all these other things. And so we call this the database model, and it's best thought of as a contract. Okay, we're going to talk into this file. There's going to be magic things that are stored in here. We use this database software, and the schema is our way to inform the database how we think this, how we're going to use the data, and let the database figure out the way to play it, where to put it. I'll put this thing over here, I'll put another thing over here, and I'll put a little shortcut over here. We don't care about that. We say this is the data model we're going to work with, and you, the database code, are supposed to be really smart and figure out how to make the most sense of that. So the data model is not just the SQL to query it, but the data model is our contract about the shape of what we're going to store and retrieve in our database. So there's a number of common database systems. I've mentioned several of them. Oracle is awesome. It's a company that was effectively created just to make a database system. And they were founded at the birth of the relational movement and won because they were very good at it. The others who didn't win were like IBM and others, although they all have relational databases as well. A lot of those other vendors I don't know if letting Oracle win is the right word, those vendors that that Oracle outcompeted were the ones that didn't embrace this relational stuff. Because I was in college when they saw was coming down, and some of us were like, relational, too much math, give me the quick, dirty stuff, right? And it took a while for the relational model really to win, but when it won big time. And Oracle was a company that made a bet on it winning. And so by the time we all realized, whoa, it's a good idea, because we all thought it was a bad idea, or at least I did, it was too late. Oracle had the best implementation of the good idea that we all finally realized was a good idea, and so Oracle kind of wins. So then what happens is Oracle's kind of the old dog in the marketplace, the very expensive commercial. A lot of people think it's simply the best, but there's alternatives that are quite nice. There's MySQL, which is an open source. MySQL has been purchased by Oracle, but continues to be open source. If you really want to be open source, there's a MySQL MariaDB. MariaDB. It starts with an M on purpose so that it starts with the same letter as that. And so MariaDB is a copy of the open source version of MySQL, which was made at the moment that MySQL was purchased by. But MySQL remains open source, so a lot of people who use MySQL are switching to Maria, but a lot of people just keep using MySQL. And if Oracle does something bad with MySQL, we'll all switch to Maria, and that'll be the end of that. So at that point, Oracle hasn't done anything really bad with MySQL, and so it's okay. So we tend to use MySQL for online websites, a lot of website stuff. Oracle tends to be used for enterprise kinds of things. And then another one that's very popular is SQL Server. It's the Microsoft one. You may have even used Microsoft Access, and you might have even done like a screen where you're dropping things down that turn out to be SQL under the covers. Don't know. SQL Server for Microsoft is a very good product. Some enterprise organizations are all Microsoft, and so they use SQL Server. Don't feel bad. Pretty much everything I'm going to talk about applies equally to SQL because SQL is a standard, and that's nice. There's another one called Postgres that's also open source. That's very nice, and it's kind of more of an imitation of Oracle than MySQL. MySQL is designed to be simpler and faster and solve less problems than Oracle, but do them super fast, and that's why it's often very popular in websites. Postgres is sort of more of a rich database that's very, very much a direct competitor to Oracle. MySQL is its kind of own world. And we're not going to use any of these. If you go take sort of a web class, you will probably use MySQL, and everything I'm going to teach you in this class is useful there. Okay, all the knowledge, all the SQL. But we're going to use a thing called SQLite. Light meaning little, tiny, not very heavy. And so SQLite is what's called an embedded database. And MySQL or Oracle are whole pieces of separate software that we sort of talk across a network connection to. But SQLite is actually part of software. And so it's built in. Your car, if it's a reasonably modern car, probably has 5 copies of SQLite in it, right? So your car has SQLite. If you have a fancy music player in your car, it probably is using it. If you have an iPhone, it probably has 30 copies of SQLite in it. Because SQLite is designed to be really small, so small that you actually don't have to separate it, you just build it into the application. And the thing that matters most to us is that it's built into Python. It's already there in Python. So that's super awesome, right? And it's fast and aimed at smaller amounts of data, but because in Python we're doing data analysis, we will make good use of SQLite, and the fact that it's built in just makes our life really simple. We don't have to install a bunch of software. Python has it with nothing more than an import statement. You know how this story goes. If you're in Python and you got to get something done, the first thing you do is figure out what import statement you need. Okay? So that gives us a sense of the SQL applications that we'll be using. Up next, we're really going to start writing some SQL, make a database and put some tables in and put some data in those tables. So now we're going to get to the heart of the matter. We're going to actually write some SQL and we're going to make a database. Okay, you hopefully by now, I've told you a couple of times, install the SQLite browser. If you haven't, do it. You could also write a Firefox plugin that can be used to manipulate SQLite databases. I used this before SQLite browser came out with their newest version. So everything I'm going to do could be used by either one. And there might even be a way to do it with a SQLite admin tool if you've downloaded like a MAMP or an XAMPP. So it doesn't matter. You just need some piece of software that gives you a place to type SQL. You hit a go button and it sends it to the database and comes back. That's all you need. Okay, and so this is what it looks like, SQLite browser. So let me go ahead and start this thing up. SQLite browser, and there we are. Database browser for SQLite. And what it basically does is this is going to read and write a file, and that file that it's going to read and write is in a very specialized format that's highly optimized for rapid retrieval and rapid storage of data. And so we'll start by saying new database, and I'm going to pick a place on the disk. I will put it in the desktop and probably point them for everybody. Databases, and I'll call it SQL1. That'll just be the name of the database. Now it's writing to a file. This file is not something you should read using anything other than SQLite library. It's a funky looking file, so we're going to save it. Boop. And it's asking us if we want to create a table. I'll just hide that thing. So we have no tables, no indexes, no views, no triggers, no nothing. And we have a place that we can execute SQL. So when I said you're a database administrator, we've got a file back there called SQL1 that everything we do is actually reading and writing to that file, but we don't write code to touch that file directly. We always are using the SQLite library. Okay? So we're up. Let's create a table. Now, this is our first SQL. And so create table, and then the name of the table, users. I'm just going to use uppercase. Upper lowercase generally matters. There are a few weird situations where it doesn't matter. So just pretend that case matters in this situation. And it teaches you something right away about SQL. SQL is designed to be somewhat conversational. And so the keyword create table is kind of like one keyword. We're creating a table. Then the name of the thing, and then a parenthesized list of the fields and then the types of the field. That's what we're dealing with. So this is create table named users,
and we're going to put 2 columns into it, and one is a variable length character, 120 up to 128 characters, an email that's also a variable length character up to 128 characters. So this is sort of our schema. This is our contract. We're saying these are the only 2 things we're putting in this table. We can't put a thing called age in the table. We can't put a thing called favorite beverage in the table. And we can't put 129 characters in the name column. We can put 0 or 1 or 2 or 127 or 128. That's just fine. But we can't put 129. This is a contract. And the database, if we want to put longer characters in, we just say, no, we want to put 1,024 in. And then the contract will be, we could put up to 1,024. And if we put 1,025, the database would be mad. And you're like, why do you do this? Why is it, why is the database so obsessed about this? And the answer is, as it lays the data out on this disk drive and it wants to get to it fast, it really is helpful to know the size, the maximum size. Because if you say this is only going to be 4 versus 4 megabytes, it might lay the table out differently on the disk. You don't need to know that. You just need to be explicit about the contract. Okay? So this is part of making the data model, figuring out in advance the kind of data that you're going to use, how you're going to use that data, and then you communicate that to SQL, and then you don't worry about all the magic that makes that super fast. So this is the contract that you make so that your data is really fast. By being very explicit about your data, you get in return, the database does a lot for you and does it really fast. So now I'm going to go into my little SQL window, and I've pasted in that create table statement. And different user interfaces will have different things, but they all kind of have a window, and you all put some database stuff in them, and then you hit this execute button. It's a little play button. In this one, it might be something else in yours, but at some point you go, do it. And down here it says, query executed successfully, create table, yada, yada, yada. So now if we take a look at the data, we see that we have one table, and the table is named users, and there's name and email. And if we pull this over, we'll see that the varchar is 128. So the database knows the contract that we just gave it. Okay? So that's your first SQL command. Your next SQL command is, and you probably should just copy and paste this stuff off the slides. It's what I'm doing. So there's your table. We're going to put some data into it. And so let's go ahead and do that. And we can put a new record in there. We can say Chuck csev at umich.edu. We can say another new record. We can say Colleen. We'll call her VLT at umich.edu. I want it so these sort right, edu. Another record, we'll make this be Sally at umich.edu, and then we'll have another one we'll call like Fred. I don't know, Fred at umich.edu. Now it turns out that everything we're doing is actually running SQL, and I'm going to finish that. And if you take a look here at the SQL log, you can see all the SQL that's going on right here. Just insert, but let's kind of leave that alone for now. We'll just kind of hide that. But that's what's going on right now. And so we made a table, and it now has 4 rows in it. And now we're going to do some SQL we've done the create, now we're going to do some inserting and deleting and retrieving of the data. So the first thing we're going to do is insert another record. Now, what we were just doing in that user interface was exactly this. Here is another example of some SQL where insert into is kind of like a single keyword, the name of a table, a parenthesized list of the columns, and then the word values. That's just part of SQL, and then a parenthesized list of the corresponding values. So Kristen is the name, and kf at umich.edu is the email address. And so that is a SQL statement that inserts a new record into our users table. So we'll just cheat and grab this, copy it, and then go to the SQLite browser, and we will go to execute SQL. And I will get rid of the create table because we already did that, and just type in insert users with that parenthesis. It's doing syntax coloring for me, which makes it very, very helpful. And then, if I got the right SQL, now let's just say I make a mistake. Let's just say I call this zap instead of values. I will run this, and it'll go like zap is a syntax error. And so it does talk to you, and then you can go fix that and say values. And it's actually helping me, and then I can run that. And then it says success, and I go back and look at my data structure. I can browse the data, and there's Kristen, right? So the insert added another row. Pretty simple stuff, isn't it? Okay, so there we go with that. We inserted another row with Kristen in it. Now we can delete a row. And so we say delete from, which is again kind of like a keyword. Delete, it could be delete users, but it's sort of like we're not actually deleting all the users, we're deleting something from the users. And so they add this keyword in SQL that's kind of redundant. It's not necessary, but it lets us read it a little. Delete from users. Well, it sounds like words. Sounds nice. Delete from users, the name of the table, and then a where clause. And you can put where clauses on lots of different SQL statements. And that says, don't delete all the rows, only delete where this is true. And in this case, we put a logical question. So this is like a question mark in an if statement, right? Delete from users where email equals ted@umich.edu. This could be one row, or there could be 100 rows that all have that email address. That would actually be bad to have 100 rows that had that email address if it were a key, but whatever. So that just says delete from users where email equals ted@umich.edu. So let's do that. Again, I just copy this, copy, go back to my SQLite browser. I could use the delete record button, but I'm trying to teach you this SQL language now. So this is the way to do it. Delete from users where email equals ted@umich.edu. I hit the play button, and it says executed successfully. And I go back and I look at the data, and was there no Ted in there? I better delete a different one. Let's call Fred. Let's call it fred@umich.edu. So now if we do the browse data, Fred's gone. So the delete works. That's why I do cutting and pasting on this. So that's a delete. Update allows us to sort of reach into a particular cell or set of cells in a table, many rows or many columns or many row column combinations, and we just say update, which is the SQL keyword, the table name, set, which is an SQL keyword, and then the column name, and then the new value. The where clause is important because without the where clause, it would do it for all of the rows. So the where clause reduces the rows. So we have a where clause here that says where email equals csev@umich.edu. So what we're really saying is go find the rows that have that true and change the column name to be Charles. Okay, the column named name to be Charles. So let's do that one. And hopefully at this point you're sort of following along and you're doing your own data, because that will be one of your assignments, is to make a database and turn it in. So I will say execute, boop, and I take a look at browse data, and you see that Charles is now changed. So far so good. You see why I really like this language? I mean, it makes so much more sense than Python. But don't criticize Python. Don't be hating on Python. Python is powerful and flexible. This is powerful, but not so flexible. So we did a insert, we did a delete, we did an update. Now we have to do the read, the R part of CRUD. And so that is select. And select takes a list of columns. That's a column list. And star means all the columns. From is a keyword, and then users is the name of the database. And you can have either with or without a where clause. And so this says select. That really says all rows, all columns from the database named user. Select star from users. Okay? And this says, so this will turn out to be one row in our little database, but it might be more than one if this was true, if this where clause was true for more than one. Okay? So let's run those commands. Now it turns out that we're kind of implicitly running those commands, the select star from users, every time I hit that browse button. Whoops, don't do that. So if I go over here, and when I do browse, I could actually see that in SQL log, the last thing was that, okay? And so that's it's doing a select on our behalf, but we're learning how to do SQL, so we want to do it the hard way. So we say select star from users, hit that, and now down here we see that, and we also see in this log as the log goes by that it sent that stuff. Now it's also sending more stuff. We'll get rid of the log. It's too complex, but it's really just SQL. I'm giving you the simple stuff at the beginning. Okay, so that was a select, and I can add a where clause, where email equals csev@umich.edu. Let's see if I type that right. And that should show us all those rows, but only show the ones for which that's true. So that's a where clause. And a select. You can also throw another clause on the end of a select, or you can have an order by. So in this case, I'm going to select star from users, which is exactly what I did before. Select all the columns from the table users. Order by, again, a two-word keyword that rolls off the tongue more naturally. Email, which is a column. Sorting is one of the things that databases do really, really well. And that's because it actually sometimes, for sorting, it has these things, and then it has these little tricks that say, oh, that one goes here, and this one's the next one. And so if you really want it in sorted order, I have a really quick way to figure that stuff out. But that magic, you don't worry about. That's the database's problem. So you just say, hey, smart database from billion-dollar company, I would like to order this by email. I don't know how to do that. I don't even know how to write a sort algorithm. I just know that I want it ordered by email. Now, do it, database. And there you go. And you see these things ordered by email. And if I want to change it to be ordered by name, it's ordered by name. Okay, so name this time, email that time. Turns out sometimes you can just click on this header, but we're learning the tough way, which is actually not all that tough. So you can select and you can order them. You can have a where clause. And ultimately, this is the summary of what I've taught you so far. An insert into a table with columns values, a delete from users where, and a true false with update users set, select star from users, or select star with an order by. So at this point, you'd be like, wow, I needed to go to college to learn this. It's like so easy. Ha ha ha. It is easy. That's why I don't teach you SQL until later. So you learn the hard stuff, so you're tough. Now I can show you the easy stuff. Now, of course, there's some complexity to come. But at the end of the day, when we're talking about a single table and the statements that are one table, it looks like a really big, fast, smart spreadsheet. And that's why some of you may recognize what you're learning here. You may say, you know what, I've actually been doing this, and I didn't realize how smart I was. I didn't realize I was doing databases. But we're still just at the basics. The power comes with what we're going to talk about next, and that's when we have more than one table and we start modeling data at the connections between things. And that's when we really start to show how you can make things really fast, when we exploit the relationships between tables. So that's what's up next.
Hello and welcome to a code walkthrough. In this bit of code we're talking about the emaildb.py. This is a beautiful little example in that it sort of reduces talking to the database to kind of its pure essence. And so we'll start out this code and we import the SQLite 3 just to get the library there. We make a connection, and in databases we sort of end up with an open that's two steps. There's the connection to the database, which checks access to the file, and the cursor is kind of like our handle. It's not as simple as you just open it and read it, but you open it and then you send SQL commands through the cursor, and then you get your responses through that same cursor. So CUR here is the variable that we're interested in. And the first thing that we're going to do is we're going to we've got this file. It will either create this file, and right now this file doesn't exist. It's going to be in the same directory. Oops, email. Yeah, there's no email DB. So this is actually going to create the file when it runs. And then the first thing we're going to do is drop the table if it exists. Drop table is a bit of SQL. The if exists just keeps this from blowing up if we start with a fresh database. And in this case, there is no file there, so we are starting with a fresh database. So this will accomplish absolutely nothing, which is just fine. Now we're using triple quotes here. I'm just kind of using that to make this a little bit easier to read. I probably could pull those lines up a bit. This one's actually small enough that I could, maybe I'll just do that. Let's do that. Let's bring that baby right up and turn this into a single quote. That's short enough, right? But triple quote is just, this one here is a little longer, so I use triple quote. So we're going to drop table. That's going to do nothing first time through. Then we're going to do a create table. Now sometimes your application will have like a README or something. It says go run these commands to set the database up, but we're able to just set this database up in this particular application. We'll see later ones where we're going to leave the database and not start it fresh. And in this one, we can do the same. And so, but this one, in this one, we could, but we're just going to start fresh by dropping the table. So we'll create it. We're going to have a email and an account. We're going to, basically what we're doing here is we're really going to pretend that this is a dictionary. If you recall, when I said dictionary, dictionary is like an in-memory database. Well, now we're using a database to do a database, but the first thing we're going to do here is pretend it's a dictionary. So that's a little crazy. So these next lines of code hopefully are pretty familiar to you, right? Get a file name, loop through it, check to see if it's grab inbox short by default, so we can press the enter key and then loop through it, right? And so this little part right here, this is our basic loop that we're doing, and so that is pretty normal. And if we look at this line right here, that line right there is the line that is that line right there makes sure that we can only get the from lines. We've done that a bunch of times, and we're going to split it. We're not going to strip the right because the split's going to take care of that. And then we're going to grab the email address, which of course in the from line is the second part, and then we will have that. So now we're going to do some database. So the first thing we're going to do, this bit right here is kind of like the dictionary part. So the first thing that we're going to do is we're going to select count from our database, that is an integer, where email equals. And this part right here bears some explaining. This is going to be c7@umich.edu or whatever. Now, it is dangerous to put those strings, especially from user-entered data, into your SQL. You technically could. I could make this be a email equals single quote c7@umich.edu. I'd have to escape the quotes and stuff. But this question mark is a placeholder. And this is a way to basically make sure that we don't allow SQL injection. Go Google SQL injection to get a sense of what that is. It's more of an issue in online applications, but in this application we're just being good. And so the way this works is this is a placeholder in this SQL that will ultimately be replaced by this. Now you could have several question marks. We only have one in here. And so you give a tuple. And if we just put email, it won't turn into a tuple. This is a one tuple basically. This little weird parenthesis email, comma, parenthesis, that is a tuple with only one thing in it, and that's just the weird Python syntax. It's rare that I apologize for Python syntax, but that's a little bit less than pretty, but it's okay. It's a tuple. And normally, if there were like two of these, then there would be email, name, da 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 da. Okay? So this cur.execute is actually not really retrieving the data. In a way, it's looking at the SQL and making sure that maybe it might verify that the table name is right, or if there's any syntax errors, etc., etc. So this actually is not really reading the data. So, but we have prepared this cursor. This is kind of like the opening of a file, but what we're opening is a record set. We're opening a set of records that are going to, be this wherever it's true. So it's like we're going to read this like a file. Now later things will loop through this, but we're only going to say, hey, grab that first one, right? We could have even put maybe a limit clause on there or something. Grab the first one and give it back in row. And so row is going to be the information that we get from the database. And so that is, if there are no records that meet this, then row is going to be none. So here's kind of, again, like the get. Here's like the get, where if the row wasn't there, because the way we're doing this is we're going to end up with this row in the database. Here's this database, and there's going to be 2 columns, and there's a bunch of rows. And then here's going to be CSEV 4 and Jen 3 and Stephen 6, right? So these are the counts. And so we're grabbing this variable out, if it's CSEV that we're grabbing, and that's going to come into here, right? That's going to show up in here. And that row is actually, it turns out that the row is a list, but we're only getting one thing. And what we really are doing is if we search through and we got through and there was nothing, then row is none means that there was no, and we're seeing like Chen's for the first time, and we have to insert it. So if row is none, we're going to run an insert statement, insert into counts, email count. Now we've got to set it to 1 because it's the first time we've seen it. So values, and then again the question mark. The question mark basically says, hey, I'm going to have a value in this tuple, and there's an ordering to the tuple, and so there's only one question here, one question mark placeholder here, and then 1 is the initial count. So email question mark count 1, away we go. And so then we have a tuple that gives to this execute statement, just like in that execute statement, the corresponding sort of strings or integers that are to be replaced by each of the questions. So when this runs, there's going to be a new record, and there's going to be a 1 that's put in there into that new record. If, on the other hand, we pull back a row that exists, we're going to get this 4 number. And you might think we want to take this 4 number and add it, but in databases, it's always better to do an update because there might be multiple applications that are talking to this database at the same time. So no matter what update does is in a single atomic operation, it turns whatever this number is into 1 higher, and we don't have to worry about other pieces of code potentially modifying it. Now in this case, we don't have to worry about that because we're the only piece of code, but using update to increment something is way better than reading the value and then doing an update to adding 1 inside of Python and then updating the new value, that's 2 SQL statements, but it's also not atomic, okay? So if the row is none, if the row exists, we just know that it exists, and we just want to add 1 to the number. We do have the number sitting here in the row variable, but we don't need it. And so we're going to say update counts, set count equals count plus 1, column name, where email equals, and then another placeholder, and then another tuple for the question mark, okay? And so that's what this little bit of code does. That is kind of the read it, parse it, check to see if it's there. If it's not, insert it. If it is, update it. And so then we see this con commit. And this con commit, basically the way it works is that the database is efficiently keeping some of the information in memory, and at some point it has to write all that stuff out to disk. So you can choose at times where you put this commit. Right now we're going to commit every time through this loop, but you might commit every 10th time through the loop because the commit will take some time because it forces everything to be written to disk, and these can run really fast, and the commit is the slowest part here. So sometimes we do things like commit every 10th record or every 100th record. If it's an online system, which is not what this is, you have to commit at the end of every sort of screen paint. But for this kind of a system, because we're putting so much in, this is kind of a bulk insert, we might come up with a thing where we, every 10th time we do a commit. But ultimately what this will do when this is running is it will build up slowly but surely, adding new records, and then 1, 1, and then it'll be a 2 and a 3 and all these things, and add another 1, that'll be 1. It'll do this thing, right? And then at the end of the day, that is what's going to be in the database. Now, so let's take a look what's in the database, and now we can actually read the database. And so in the database, we're going to run a select, and we're going to select the email and the count from counts, order by count, descending. So look at that, isn't that cool? We're getting in the top 10 because databases are good at sorting, and they're good at all these other things. So we're going to then execute this, and then we're going to ask for the rows one at a time, and the rows are going to be a tuple, and row sub 0 will be email, and row sub 1 will be count. So we run all this stuff, and then we close the connection, and away we go. Okay? So let's go ahead and run this. Let's go ahead and run all this stuff. Python 3 emaildb.py. It asks for a file name, mbox short. Well, I can hit enter, right? Mbox short. And that's it. And it looks just like that, and it counts it, and away we go. Now the difference is, at this point, we have a file, emaildb.sqlite. And we can run the SQLite browser. And we can then open this database. And we can see what's in there. So here we go. It has made an SQLite database. We have a table of counts. And then we can take a look at the data. And there we go. We've got the data and we can do this. And so let me close this. It's important at times when you don't want necessarily to have, well, let's see if we can cause it to lock up. Let me run this again, and it's going to drop this table. So I'm going to run the code again. But this time, I am going to do the full one, mbox.txt. Now, we'll see what happens here. But it ran. And now, so what we have to do then to see this date is from the previous run, but if we want the most recent one, we hit refresh, and then away we go. And so we can see this stuff. And so this is just a real simple start to see how you can connect some of the stuff that we've been doing, but store the data in a database. But the nice thing about the database is that it can store this stuff from run to run. Even though in this case, we're dropping the table every time. In later things, we will see how we can store data from run to run to give ourselves more restartable processes. Cheers.
And there were products that are growing from wild. And then we realized that, hey, I want to buy a product. What kind of a feature do I need? Another one of the things that I have done is the feature analysis. So we have about half a dozen of products. And the standardization are really building a consensus. We brought from a matured technology that are ready to be standardized, where people say, do I buy IBM or do I buy Oracle or shall I buy a cheaper one? This kind of a decision started emerging. And the selection of how many variety of application you can build on top of a software foundation, what I call database management system, is too varied. And so you want to have some sort of a standard so that your application can work on different platforms. We work with files, and we call it the file system. The files were hierarchical. There was the IMS, the IBM Information Management System, which is a tree structure, and the debate was going on whether there should be a tree or a network or flat file, and we are still debating whether the data have a self-describing tag, and later on we known it as a metadata, and now people call it the schema. So the database system study group come up with a reference model or a specification for a minimal functionality of a database management system. In order to be a database management system, you want to be able to store data, retrieve data, modify data, organize data, delete, manipulate data, and it becomes a spec. And during that time, there was we initiated a birth of an ANSI group. It's now called NSIDE. The ANSI is American National Standards Group, and it's called the X3H2, of which Don Deutsch and people like Lang Gallagher all participated in that. That group is called the Data Management Language. In order to standardize anything, you realize that you can have a lot of light bulb, for example. You can have red light bulb, white light bulb. The only thing you want to standardize is when you want to talk to another person, a communication interface, or a area where both of us have to understand a common vocabulary or whatever. So the only standardization of a software system is not the capability, but the language. And relational database at that time was IBM, Chris State, and he's talking about normalization. He started talking about flat file, and he called it a table. And it's a very easy concept that everybody understands. So in order to retrieve a table, you say select from a column such as such, from a table of employee. And there was a birth of a simple query language. Testing part is also a very important aspect of when you adopt the standard. You want to certify that the product conform to such and such version of ISO standard, JTC1, whatever it is. So that gets to be, otherwise your app won't work. Your application, let's say you build a student course record, and no matter, you got an Oracle, you got a Sybase or Microsoft SQL, you want your application to work no matter what. And that's what the marketplace wanted to go. The user, of course, Oracle or Microsoft say, buy my product. Oracle will say, buy my product. And in the procurement, you say, I want to be compliant with SQL. And so you have to have the conformance testing certificate. And we have the NAV labs. It's a laboratory that's certified and give you a validated product list. Here are the list of products that has been validated that they conform to it, and you can buy from that list. But there is a requirement. This is strictly user. You're buying because you're paying the money, not us. Timing is everything. You can't standardize a thing too early, or you drive a lot of innovative concept away because people say, hey, there's no way for me to get into your market because you already decided, and even though it's not very good, I won't get into that business. So you killed innovation. And if it is too late, you miss the opportunity. You get too many variety of things coming up, and the choice is too much. But of course, SQL is one of the success stories that NIST we have.
Hello, everybody, and welcome to Python for Everybody. We're going to do some code walkthrough, and if you want to follow through with the code, you can download the sample code from Python for Everybody. And so the code that we're going to play with is the Twitter spider code that is both talking to the Twitter API and talking to the database. And so what we're going to be doing is we're going to run code that's going to hit the Twitter API, much like we did in a previous chapter, and we're going to retrieve the data, but we're going to remember the data so we don't have to retrieve it again. Okay, and so we're going to keep track of people's friends, and what we're doing here is sort of illicitly pulling down, slowly but surely, based subject to our rate limit, we're pulling down who our friends are. And so let's take a look. We're going to use URL-lib and URL-lib error, Twitter URL, which was code that augments my URL to do all the OAuth calculation. We're going to get JSON data back. We're going to make a database, and we have to import SQL because of the way Python doesn't trust any certificates, no matter how good they are. So this is our URL to talk to the Twitter API. We're going to make a database, and again, the way SQLite works is if this spider.sqlite doesn't exist, it creates it. And we get ourselves a cursor, and we're going to do a create table. This, if not, exists. Some SQLs, but SQLite 3 does this. Create table if it doesn't exist. We want to start this over and over. Unlike the tracks example, I want to start this over and over and not lose data. And this is a spidering process, and we'll see a lot of these where we want a restartable process where we use a database. So if we're starting with nothing and there's no file, a spider SQLite, it creates this table, and it's the name of the person, whether we retrieved it or not, and how many friends this person has that we know of in our database. Now this little bit is to deal with the SSL certificate errors. The certificates are totally fine, but Python doesn't trust any certificates by default, which is frustrating, but whatever. So here we're going to have a loop. We're going to ask for a Twitter account. We have to type quit to quit. If we hit enter in this case, we're going to actually read from the database an unretrieved Twitter person and then grab all that person's friends. Okay, and so then we're going to do a fetch one, get one, and that's going to get the name of the first person, the sub-zero. If we had more things than name here, sub-zero is the first of those. Fetch one means get one row from the database, and sub-zero means the first column of that first row. And if this fails, then we've retrieved all the Twitter accounts. And so, we're going to augment this Twitter URL using this makes, you can look at the twurl.py code. This basically requires the hidden.py file, which has your keys and secrets in it. You got to get hidden.py updated. I've got it updated, but I'm not going to show you because it has my keys and secrets in it. And so we're only going to take the first 5, which means we're probably not going to find friends of friends of friends. It's only the most 5 recent ones. We could run this with a much higher number to get to so we have more than one friend. We'll show the URL while we retrieve it. We will do our URL open, we'll do a read, and then we'll do a decode to make sure that this will give us data in UTF-8, and then decode will give us data in Unicode, which is what we need inside of Python. We will ask for the headers from the connection. We'll say, give me the headers, give me a dictionary of the headers, and the X rate limiting header from the Twitter API tells us when we're going to be told we can't use this API anymore, because this is one of those things. And then we're going to parse and load the data that we got from Twitter and get a I think it's a list. Yeah, it's a list. And then we could dump this if you want. In yours, you can undo that. And then what we're going to do is we've just retrieved this person's screen name and their friends. And so the first thing we want to do is update the database and change the retrieve from 0 to 1. And that's because we're going to use this to know about unretrieved. So retrieved being 1 means we've already retrieved it, and we did retrieve it. So for that account, we've retrieved it. And then what we're going to do is we're going to parse that. And so this is similar to the Twitter code we did previously in the Web Services chapter. We're going to go through all the users. We're going to find their screen name. We're going to print the screen name out. Okay, and then what we're going to do is see if, let's see. So we're going through all the users who are the friends of this person, and we're going to say, oh, okay, let's select the friends from Twitter where the name is the friend person. And what we're going to do is if we're going to do a curve fetch one of this Twitter, the name of the friends, this is the friends screen name, right? So we're going to say, oh, okay, if we get this, we're going to get the friends screen name, and we're going to get how many friends this particular screen name has. If we find a URL, we find it in there, we're going to do an update statement and add 1 to their friend count, how many friends they have, and then keep track. This count here is not in the database, it's just so I can print it out at the end. If there is no record for this particular friend, we're going to insert them into it new, and we're going to say, here's the new person that we just saw. Here, that's their name. We're going to set retrieve to 0, and we're going to say that they have 1 friend. Okay? And then we're going to commit the transaction, and then we're going to close this at the end. Okay? So let's go ahead and run this. The first time it's going to create an empty database. So I'm going to say Python 3 TW Spider. So ls star SQLite, nothing there. Python 3, oops, that's because I removed it. Python 3 TW Spider.py. Okay, so I'm going to start with a Twitter account, Dr. Chuck. And so it's doing this retrieval, and don't worry, showing the token and the signature is not dangerous because you don't have the keys or the token, the secrets and the token secrets, so don't get all too worried. So I have 11 calls left, so I hope this all works. One of my friends is Stephanie Teasley, and these are in reverse order. So let's grab Stephanie and ask for Stephanie's friends. So now we just retrieve Stephanie's friends, and here are Stephanie's most recent friends. And then I can just hit enter, and it'll randomly pick. Let's see if I can in the database. Let's open this up, file open database. Hope I don't lock myself. Sometimes it's a little scary when you look at the database and you're just checking. So this is what my database looks like. We retrieved Stephanie, and this is how many people. So these are the friends of Stephanie and me, and these are how many. I'm not in there. So we retrieved Stephanie, which was a friend. So let's go grab, I don't know. Let's grab Tim McKay and get that one. Remaining 10, I don't have too many of these. Tim McKay, right? So there we go. Remaining 9. And so if I do a refresh on this, then you see I've got some more folks. If I hit enter here, it'll pick one randomly based on the retrieve being 0, so it won't pick Stephanie or Tim because they're 0, but we have lots of other folks to pick randomly, and we'll hit enter. So it picked, who did it pick? It picked screen name Live EDU TV, which is ironic because I'm recording this on Live EDU TV right now. And so we can keep hitting refresh, and away we go. So I'm going to stop now because I only have 8 remaining, and so I'm going to type quit, and so we will see. We'll see how that works. So that's how it works. Now remember that you've got to edit the hidden.py file to make this work because we are talking to the Twitter API. If you don't edit that file, it won't work for you. Okay, so I hope you find this useful. Cheers.
So now we move from sort of the SQL and the contracts we need to talk to a single table to linking multiple tables together. And this is where the real power comes, and this is where the complexity comes. So up till now, it should be real simple. when you start a company, and we're going to kind of pretend we're going to start a small company to build an application to manage music. When you start a company and you're going to build an application, lots of applications need databases. And you need to design the database for your application. And often this is very much a team effort with a lot of different people with skills. Some people worry about the end user capabilities, some people worry about the performance, etc. And so database design, what I'll show you coming here is just the beginnings of database design. But the basics are very powerful. And it's something where smart people should take time in database design. And so it's a very collaborative process. And if you ultimately look at the database design for applications, we draw these crazy pictures, right? And in these crazy pictures, we are capturing, this is basically multiple tables. Table, 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 table. And this particular database is kind of about an events, like, reserving the picnic shelter at a park, right? What times, who's going to be there, who reserved it, all these other things. And what we're starting to show is that how these tables are connected together. So each of these little arrows. So these are this is a table, and these are the columns in the table. And then some of the columns are special columns that represent relationships with other tables. And we're not going to go into all the detail. You can eventually go into some of the detail where you see what this little arrow means, and that means one, and this means many, et cetera, et cetera. And there's all this fancy stuff. And so we'll talk about this eventually. But this is sort of like what we're going for. We're going for a picture of how we want our application's data to be stored in the database. And this then becomes our schema, and it's the contract. So we made one table with two columns, and that was a schema and a contract. But now we're going to make multiple tables with many columns, and some columns that are specifically there to connect from one to another. So if you're working in a large application, you might walk in and see a picture like this on the wall. And you think, look, whoa, that's really important. That must be pretty complex. And for this application, it probably represents years of clever engineering to make sure that the application runs well. But this is basically how this, I don't know what it is, open medical record system, I just kind of borrowed the picture. This is how the data is stored in its database. And these things can be very complex. In a project I work on called Sakai, it's probably 4 times bigger than this. But if you zoom in on it, which you can't, but it's just a table and some columns and some connections. And then, oh yeah, there's a table. Well, that one's kind of complex. Here's a table, some columns, and 2 connections. So yes, it looks complex on the surface, but ultimately, we're just trying to figure out which tables we are going to make, what we're going to put in those tables, and then how we're going to connect the tables together. And the connections are the thing that make these things so powerful. We could just put all this data in one file, but then this thing would run like terribly slow. And so the trade-off of thinking through how your data is going to look is that when you're done, it's fast. A lot of times we don't worry too much about how fast your program is going to run, but when it comes to scanning data, especially if it's a lot of data, you think about that a lot. So the whole idea is to figure out the data that you need to represent and then drawing a picture and then lines between those pictures, right? And the basic rule that we're going to use is don't put the same string data in twice. So for example, if we have a column of something, don't put Chuck in twice. So that's bad. So if you have some column and you're replicating the same string data twice, that's not good. What you want to do is you want to make another table and put a Chuck over here and give a number to Chuck like 1 and then put 1, 1. So to indicate that something belongs to Chuck, which means you're modeling data at a connection between one table and another. We'll go through this in super great detail. So the basic rule is don't put the same string data in twice, use a relationship instead. And the other thing is sort of like model the real world. If you have users and tracks and Christmas tree farms and whatever, you'll have a table for the Christmas tree farms, and you'll have another table for the Christmas tree types, and you'll have another table for whatever. And so often you're starting to sort of build an application. And so the application that our little company is going to build is an application keeping track of audio. Our company has decided that people don't use albums anymore and aren't interested in buying whole CDs of music. So we're going to sell music by the track. I think this is a great idea, and I think we're all going to get rich with this little company. And this is the user interface that I invented, or I screenshotted from another vendor's. But whatever this is, this is the program we're going to build. We're going to make a track-making thing. Now, just looking at this user interface, we see some problems right away. And often, if you try to just turn this into a spreadsheet, these things would become the problem. And the problem has to do with replicated data in columns. And so it's like, great, this is all cool, until you have the same artist name in the columns. That could be once or hundreds, because Black Sabbath has written hundreds and hundreds of tracks. And then even in the album column, that's a problem. And then it gets even worse when you're in the genre column. You're putting this string in a zillion times. And if you've been writing Python programs, they kind of finish really fast. And that's because the only assignments I've given you are tiny. But when you're going to do 1 million or 1 trillion things, the difference between metal and the number 2 to replicate this is actually very significant. Because this isn't just a 6 or 5 character string. This could be a very long string. And so in your data, you have to allow for very long strings. And so these are the problems right there, all this replication. Now it turns out that we have a user interface person in the room, and the user interface person, we say like, hi, we're a database expert. We took a class online and we know that you're not supposed to replicate data. And the user interface person says, oh no, this replicated data, we've done surveys, and that's exactly what the user wants to see. And you can't argue with that. If that's what the user wants to see, that's what they see. But we still have to write an efficient application. And so that's where we start going through a data modeling exercise, where we say, this is the kind of stuff we want to represent, and this is the kind of user interface we want to support. How can we build a really good data model? So it's not like you've got to change the user interface to make it good. You change the data model then to represent the stuff we want, and then construct it in a way that the user interface is exactly what the user wants. So the idea is you look at the data that your application is going to look, and we got all these columns, and you say, is this column represent a thing in the real world, or is it just another attribute of a thing? So there's like a thing and then attributes of the thing, or two things. And so you got to go across all of the columns. And so that's what we're going to do. We are going to look at all the columns, and we are arguing. So right now, imagine we're in a conference room, we're sitting around a table, and we're going to draw this picture. And this picture looks like the thing. It's got little boxes and lines, right? We're going to draw a boxes and lines picture. And we have a blank screen right now. So the first question actually in these meetings is commonly where to start, because you got a lot of stuff. In our simple, it's really simple. And it turns out that it's not so critical where you start. Even if you start at the wrong place, eventually you're just going to have this web of information, and it's all connected, and it'll all work out if you do it right. But it does simplify the drawing of your picture if you start at the right place. And so the way I was taught to start at the right place was to think about the thing that is the most essential to this application. What is the one-sentence description of this application? And in this application, it's a thing that manages tracks. It's not an album managing thing. It's not an artist managing thing or a genre managing thing. It's a track managing thing. And we kind of see that in our user interface. We see that every line is a track. And so that makes it easy. The first table we're going to build is the track table. And once we build the track table, then we have to look at all the other things and say, look, which of these things are themselves tables and which of these things are just attributes of track? Okay, and so it turns out that things like numbers and like stars, just a number, that's 5. These are all 5s. Apparently, I only like stuff or hate it. And then this is the number of plays. And so you go like, oh, that's part of it. That's part of a track. That's part of a track. Well, and now we come to the 3 things that aren't part of tracks because they have the replicated data. That's the red flag that says, not part of a track. So somebody gets up to the board, grabs a piece of whiteboard, and they go like, that's our first table. It's a track table, and it's going to have a rating, length, and a count. I guess there should be a title in there as well for this column here. So we have a title field, title. Okay, so now we're good, right? We've got that. The question is, what's connected to that, right? Well, what is the thing that's the next thing to draw? Well, tracks could be connected to artists. They could be connected to albums. So let's just say kind of albums have many tracks. So the next thing we're going to do is we're going to make an album table. And we're going to say on our whiteboard, we're just drawing on a board right now, we're not writing code yet, that tracks belong to albums. And now it's kind of easy that what albums belong to? Well, albums belong to like groups. Now if you're a music expert, you kind of understand that we're oversimplifying things. And that's a fine argument to have when you're starting your company. But we're going to pretend the world's simple and that tracks belong to albums that belong to artists. So we're almost done with our meeting. So we got artists, albums, and tracks. We've drawn a picture. And the question is, where does genre belong to? What does genre connect to? You know, because does genre connect to an album? Does genre connect to an artist? Or does genre connect to a track? Now you may want to go to your iTunes and go to a track and change its genre. Change it to, you know, easy listening. Now, if the track was, if the genre was connected to the artist, this is an album, sorry, it means that it would then immediately change all those to easy listening, because that means that albums have an attribute of what their genre is. If it was the same for an artist, that means that all your AC/DC would be changed to easy listening. And if it was an attribute of track, only this one would be changed to easy listening. So the question is, when you go into that system and you change one thing, does it change all of these based on the album or the artist? Well, you can go pause and go ahead and do that, but I'm going to tell you. It turns out if you change that, it only changes one. So that actually tells you. And so in the meeting, we're arguing about this. I think it should be here, and I think it should be here. And then you say, well, but if you do it this way, that means that it's going to change. And then the UI person is like, no, we can't have it connect to the album because then our users would be so mad at us, blah, 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 blah. We wouldn't make a lot of money. So when it's all said and done, you've argued through. It took you a lot longer to argue this last bit. This was the hard part, to say, okay, genre belongs to track. It just does. And this is a simple, trivial example of how the data model creates the features of the application. Sort of when we started, we saw this big picture that what's in the data model determines what the application is capable of doing. And we have to get the data model right so that it can all be very efficient. So now that we've drawn this picture on the wall in our conference room, at some point we have to map this into a database structure, okay? We're going to figure out how to actually map that logical picture that we just drew into a physical picture, exactly how we're going to represent this in a database. So welcome back to lunch, right? If you remember the morning, the last lecture, we argued, we drank a bunch of coffee, we scribbled on whiteboards, we erased whiteboards, and we argued about where the genre belonged. But when we're all said and done, we ended up with this picture. It's still on the whiteboard. We're coming back from lunch now. This is not how databases represent data. We have to be a little more explicit. There's no like belongs to magic in databases. But when you're building your data model, you don't want to be thinking explicitly too much about the database. You turn this logical model into what we call a physical model by mapping it into the database. So what we do is we just take each of the tables and the relationships between the tables, and we have to augment them with little bits of information. And so here's the track table, and so we'll make a table called track. And we take like title, rating, length, and count, and they become just columns in the table. That's the data we have to represent. And then we tend to add things to it. And so we're going to add what we call a primary key. And the primary key is a way for us to refer to a particular row. And so it's a unique number, like 1, 2, 3, 4. So each album is going to end up with a number. We'll insert the title, and the title will get a number, right? And then we use that number in a column of a different table to sort of point to it. So these primary keys are the endpoints that we're pointing to. So that we can create an arrow to a particular album, we've got to add an ID to it. So we add a primary key. And then the other thing we do is we have to add the columns that are the other end of the arrow, the starting point of the arrow. And so I'm, by convention, in this particular model, I'm naming the primary keys all ID. In track, you've got a thing called ID. And then album ID is sort of the starting point. So album is the name of a table, followed by underscore, followed by ID. Now, there's no rules about how you name these things. These could be named X and Y if you wanted to. But as we've learned in programming Python and other programming languages, making sensible names really reduces the cognitive load of understanding what the heck you meant when you were creating this. So we create a convention, a naming convention. And we have terminology for each of these things. The primary key is the key for which there's one key for every row. It's used as the way to point to that row in other tables. The foreign key is one of these columns that we add to be the starting point of the arrow. So the primary key is the ending point of the arrow, and the foreign key is the starting point of the arrow. The only other thing that we do is we may or may not designate one of the columns, sometimes more than one, as what's called the logical key. The logical key is that unique thing that we might use to look up this row from the outside world. Like in this case, the album title might be a way we'd look it up. Like, oh, where is Led Zeppelin 4? You know, type in IV and it'll search it. So Led Zeppelin 4 is going to be the title. Now, all we are doing is saying, hey, database. We're not looking these folks up by rating or length or count, but we might be looking tracks up by title. So somehow on your storage, maybe you leave some shortcuts to get to this more efficiently or more effectively. So the logical key is really our way of saying we might use this in a where clause. We might use it in a where clause. We're helping you out here. We're going to might use it in a where clause. And it also sometimes it's like we also might use it in an order by clause or a where clause. And so that's the logical key. So we have these three things: primary keys, logical keys, and foreign keys. And so if we keep drawing these pictures, it starts looking complex, but then it turns out really simple. If we take the whole data model and sort of add these primary keys, logical keys, and foreign keys to model the beginnings and ends, the beginning and end of arrow, beginning and end of arrows, beginning and end of arrows, we have to stick primary keys in all the tables. We stick foreign keys in those tables that have starting points. And then we indicate that certain things are our logical keys. It looks kind of complex, but once you've drawn the picture and you have the naming convention for what you're going to name these things, it's a surprisingly manual task. I mean, the mapping from the logical to the physical is beautifully simple as long as you have a naming convention. Now, if you walk into an organization and you took this class and you say, like, Dr. Chuck's naming convention is awesome. As a matter of fact, I stole this new naming convention from a thing called Ruby on Rails. The name of the ID, the artist underscore ID, it's a good naming convention. Naming conventions are kind of like artistic. Some you think are prettier or not prettier, but any naming convention works. And you walk in and you go like, oh, I took this class and I learned this naming convention of ID and under table underscore ID. And they'll say, well, we don't use that. We use this thing where we start with a lowercase I and then we uppercase the I track ID. That would be their primary key for a track. Or maybe they call it P track ID for primary key, right? You know, so that would be the name of this thing. And you're in this company and you're like, whoa, P track ID, that looks like crap. It's a terrible, stupid idea. Well, don't do that. I mean, this is not a superior naming convention to this other one, however they do this other one, right? What's important is that there is a naming convention, and when you work for a company, just learn their naming convention, and don't complain about their naming convention unless you get to know them, or maybe you're sort of out for coffee or something later, and you go like, well, how come you guys never did the cool Ruby on Rails naming convention? I took a class, and it was pretty cool. You know, as long as you're nice and you don't threaten them or don't tell them how dumb they are by choosing the wrong naming convention. So now what we're going to do is we're going to turn this into a new table, okay? And so I'm going to use the wizard to make a new table in our little database. Let's go over to, we're still in our database. And I am going to go to database structure. Where's the new table button? New table, new table. File, new table, create table. There we go, edit create table. Okay, so we are going to create a table, and I need to kind of look at, for my cheat sheet. We'll start with the artist table. The artist table, and we're going to add a field to it, and we're going to name the first field an ID field, and it's going to be a number. We're going to say that it's not null, it's a primary key. We're telling it that we're going to use this a lot, and if we're linking into this table, that means we're using it a lot. Auto increment, it means that we as the programmer don't actually have to specify this value. It's going to be automatically specified, because pretty much 1, 2, 3, 4, 5 are the values that we're going to use. And then unsigned is whether it's positive or negative, and for this one I'm going to leave that off. The other thing that's in our little table, let's go back and look at our little picture, is the name. Add another field, and we'll name that name. Oops, lowercase name. And we will make that a text field. And in this case, we're not going to give it a length. And there's a way later we'll give other ones lengths. And then we're going to hit the OK button. And when it's all said and done, we have an artist table. Okay, this is our old users table. This is our artist table. We could make a whole new database if we wanted, but we're not going to. We'll just kind of put all these things in. Actually, let's just get rid of this table. Get rid of users, edit, delete table, goodbye user table. That was from the previous lecture. So now we have an artist table. Okay, so that's the wizard way of creating a table. The next table we're going to create is the genre table. Now, the idea is we tend to work from outward in, the leaves of this tree outward in. So we created the artist table, then we'll create the genre table, then we'll create the album table, and then we'll create the track table, because you kind of want to create the ends of the arrows before you create the beginnings of the arrows. Okay? So we'll create the genre, and now I'm just going to use the SQL because that's a lot quicker for me to type. Here's the create table. We're going to say that this guy is an integer, it's not null, it's got a primary key, and it's auto increment, and it's unique. And that is our way of saying give each row a little number. So I go to execute SQL, and I put this bit in here. And then I run it. It worked. And if I take a look at our browse data or our database structure, genre's in there. And genre has 2 columns, ID and name. And then we have the other tables. So now we're going to create the album table. So the thing that's different about the album table is that the album table is our first example of a foreign key. So this is our foreign key. We've been putting primary keys in every table. Primary key, pretty much just say this over and over and over again, this long integer, not null, primary key, auto increment, unique. Just say that over and over and over again. Now we're going to have a foreign key, which is the start, the foreign key, primary key, right? And so we're just going to call that an integer. In other databases, you can add some stuff to it to talk about what to do if the parent thing, but we're not going to do that for now. We're just going to say that's an integer, that's the starting point of an arrow, and we're naming it artist underscore ID just to jog our memory that that's what's going on there. Go to execute SQL, paste it, run it, poof, she works. Database structure, now we got genre, and let's look at the last one. Okay, so the last one is the track. Okay, so create table, the name of the table. We've got this sort of thing that by now we're cutting and paste a bunch of times. We have a primary key, we have a logical key, it just happens to be green, it's text, and then we have 2 foreign keys, because if you remember, there were 2 arrows coming out of track, both to album and to genre. So remember, album underscore ID, genre underscore ID. Naming convention is your friend. And then we just have some stuff that's integers like the length, the rating, and the count. And we put those in. So now we have the columns and the rows and all the foreign keys for track. And then we will run that. And if we take a look at the data, we will see we got all of them done. Album is now complex with all these things. Wait a sec. Did I not? What did I get wrong here? Oh, no, track is the complex one. So track has a bunch of stuff. So there we go. So if we take a look at, we've got all of these things, and we have translated our logical model into a physical model, and we translated the physical model into a series of create statements, and we run those create statements, and now we've represented the various kinds of tables that we want to insert data into. So we're going to stop here, but next we're going to start inserting data into these tables. So before lunch, we developed a logical model. After lunch, we developed a physical model and sort of implemented it in the database. And then we, went home for the night. Now it's next morning, and it's time to insert some data into our tables. Now you got to remember all the keys and fields and stuff like that. Just like we're inserting data from kind of like the outward simple things to the more central ones, we're going to do the same thing when we insert data. Okay, and so we're using insert into, and this is a good time to point out that the keywords inside of SQL, like insert into, the case doesn't matter. The names of the tables, the names of the columns may or may not matter, and the actual data you put in, that's case sensitive because that's your data. So I'm going to type insert into artist. And the key thing that is important here is we're not specifying the ID field. So if you recall, in the artist table, we have an ID field and a name field. But if you look over here, the ID field is an auto-generated field. It's not really showing up very well because we don't have the type. So the ID field is auto-generated. So when I write this SQL, I don't need to specify the ID because as part of our contract, we made a contract with a database that says you assign that. So I'm going to run this now, insert into artist with a name of Led Zeppelin. And if then we browse data and we go look at the artist, it's added the number 1. Kind of predictable. You can kind of guess what the next one's going to be. So the next one thing we're going to do is we're going to insert another artist in, and we're going to insert AC/DC in, and we inserted that. Now, if we go take a look at data again, we got 2. And if we did a new record here, it would automatically provide this for us, right? And it would let us change this, but it would want to pick the next number 3. So what we've done here is both inserted the record, but we've also established for within this database a new number. 1 means Led Zeppelin, and 2 means AC/DC. Okay? So then, the next thing we're going to do is insert in the genre. We're kind of working outward in, and insert the value rock and the value metal. Now I'll show you a little trick here. You can actually, in this user interface of most of these things, not just this one, you can usually put more than one command in as long as you put a semicolon at the end of it. So I'm going to, if I did that right, semicolon in the end of it. So I'm going to do an insert into genre of rock and an insert into genre metal, and I'm going to run the SQL. Oh, I wonder if I did it twice. I did. So I'll just delete this record, goodbye, delete that record, goodbye. So I did 2 inserts and then I hit the button twice, so that's how I ended up with 2 copies of it. So rock, for the rest of this lecture, is the value 1, and metal is the value 2. And again, now when we're making the track table, we don't have to put rock, 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 rock. We just put 1, 1, 1, 1, 1. Because 1 is not a string, but it's a number, that turns out to be okay. So now we're going to take a look at the album. And this is the first situation where we've got to do a primary key, a foreign key, right? So we got an album table, and the album has a primary key, which is going to be automatically generated for us, and a foreign key called artist ID, because the album points to the artist. And we only add data at the starting point of these arrows, and so that's what we're doing. So this one, we have to put in title, but we don't have to put in ID, so we don't have to put that in, but we do have to explicitly put in artist ID. So we insert into album, we're going to have a title, and then we're going to have an artist ID. This number, we have to remember that 2 was AC/DC and 1 was Led Zeppelin. Now when we're doing this by hand, it's a little tricky, and you find yourself flipping back and forth to remember, like, oh, Which one was Led Zeppelin? Which one was AC/DC? And it seems like in the short term it'd be easier just to put the string in, but that's the whole thing we're trying to avoid. Okay? So for foreign keys, we have to put the numbers in explicitly because we, or the code we write, has got to remember them. So remembering what these numbers are, the 2 and the 1, is a lot easier for a program to remember than it is for you to remember doing this by hand. Now normally, you wouldn't insert this stuff. We'll have code that inserts it, and it's real easy for it to say, oh, I just inserted genre, and I inserted rock, and I got back a 2. So that actually you can get that, and so you, the human, don't have to remember this. So let's run these. So this is our first one that's doing, and I'll put a semicolon here so we can do it all at once. And I'll only push the button once. Okay, and if we do browse data and we look at the album, the ID was auto-generated and artist ID was something that we chose and title was something that we put in. So now we're in pretty good shape. Now the last thing we're going to do is probably the most complex, but it's not. We have an ID's coming for free, title's data, length, rating, and count, that's just data, and then we have 2 arrows, right? Album, pointing to album, and genre, album and genre. And so we have 2 foreign keys. Now here is where we have replication now. Those 2 are going to the same album. And these 2 are going to the same album. Same genre, same genre. It's okay to have replication as long as they're numbers. That's really the essence of what we've done. We just like went in the big circle, took replicated strings and turned them into replicated numbers. So these are okay. And so then what you're going to do is you're just going to take each of these rows that you know. Well, we don't need that. Clear. Take each of these rows, and you know most of the data. We're going to put in the title. We're going to put in the album ID, the length, the rating, the count. Put all those things in explicitly. This comes automatically, and we're going to do that. Title, rating, length, count, album ID, genre ID. Then we have the values, and then we have, these are the 2 foreign key values, and they point to those rows. And again, this is a point in time where you sort of have written down on a piece of paper what these little numbers were if you were doing it by hand. It won't be too bad. I luckily have them cut and pasted, so they're all easy for me. And if you're following along, then you just cut and paste these guys. And I'll be super lazy, and I'll copy all 4 SQL statements and run them over here, paste them in, and then I am going to put a semicolon carefully, not on each line, but at the end of the values thing. So I'm putting a semicolon on each of these guys. You don't have to put a semicolon on the last one. And I'm going to hit the run. And I'm going to look at the data. And I'm going to look at the track data. And there we are. That's all there. I can kind of move this over. And that's the track data. And again, we specified all those things. So if we look at all these tables, we've constructed them outwardly in. We started like at the genre and the artist, and we worked our way in so that we could establish these numbers so that then we could link to those numbers as we put things in the album, and then we established numbers. And so the foreign keys are the starting points, the primary keys are the ending points, and we worked in. And so we have replication of numbers in this column, but we don't have replication of strings. So the word rock, if you look at all this data, okay, that's a bad example right there. Forget that. Pretend that. The word metal is better. That doesn't count. That's just a title. That's not really word rock. The word metal as a genre only appears once in the entire database. And the thing about it is, like, what if there were 1,000,000 of these, right? 1,000,000. You say, okay, what's the difference? The word metal versus whatever, versus the number 2. If there's millions of them, it's not just that it takes up storage, it has to do with how much has to be scanned. So part of what we're trying to do in databases is reduce the amount of data that has to be scanned to get to a particular piece of information. And so the difference between metal, which might actually be 128 characters, and a number, which is actually 4 characters, that turns out to be different. And it's not we can't store it on disk drives. Disk drives are big. It's just that we can't scan past it fast enough. And we can't build indexes so we can jump past it even faster. Okay? So that's what we have achieved in this section, is we've inserted all these data and we've linked things together and we've modeled relationships and connection points rather than replicating data. So we're about to come full circle. We just created these many database tables. We've spread things out. We've linked them all back together with these numbers. And it seems like we just created a mess of everything. But now we're about to bring it all back together using the join. We finally have touched the relational power. And it may seem painful, but this is important, especially when data scales. And if what you're doing matters, then data is going to scale. You can't say, oh, my data is so small, I don't need to do this. Well, if you're doing it and it's big and you're really doing data analysis and it's like something you're doing professionally, you tend not to do small things professionally. You tend to do large things. So this notion of primary keys and foreign keys and little numbers that point to stuff, that's what it's all about. So we need to reconstruct for our user interface the data and reconnect all these connections. And the SQL syntax that allows this to happen is the join operation. And the join basically says we are selecting data from more than one table, and part of the join operation is the on clause that says when we want to connect one row in one table with a corresponding row in a different table. And so we have this example here of our data where we just want to sort of pull the artist title and the artist name out, except that the artist title is in the album field and the artist name, because we did this relationally, is in the artist field. So we don't have it in one field, so we have to pull it across two tables. So that's where we say select, and then we want the things. Now this is a syntax here where you have table name, field name, table name dot field name. The title column from the album table, the name column from the artist table, from, which is the same from we've done before, here's a table, joined with another table. And what we're doing is we're saying, let's make a super table that really is the rows of this table as well as the rows from that table. And that's what the join does. It's like, we're not going to one table, we're going to two tables. Then, in addition to the join operation saying we're going to do all these tables, the on clause decides when we connect a row in this table to a row in this table. So row to row, row to row. And the on clause that we're going to write is when the album's artist ID, that is from the albums table, the foreign key, the start of our little arrow, is equal to the ID field from artist, artist ID. So it is the destination. So this is the starting point of the arrow, and this is the ending point of the arrow. So this is the start, this is the end. So that's matching the reconnecting all the arrows for all the corresponding rows. Select these two fields, one field from each table, and then we got to glom the two tables together, but only connect the rows when this is true. For me, I would call this when. Some people prefer to write this as a longer where clause. Some databases prefer that. I tend to like using the on clause so I don't kind of confuse my where clauses. But if you learn the where clause trick, it's the same as the on clause. So let's run this one. That's already in there. Oops. So I'll run it. So here I go. I've got the title. Oops. I've got the title from one table and the name from another table. And we joined them all together, and we had an on clause that tells when they're supposed to be connected. Okay? So we can look a little more deeply into this relationship that we have, right? We can, clear this, look a little more deeply in the relationship that we have here by actually looking at all the data that's actually participating in the connection between these two rows. So here we once again have our select, and our from clause goes between album and artist. So we're this is our super row from the album table and the artist table. That's artist, that's album. And we have the foreign key relationship still. And we're going to add to this select these two fields. Everything is the same as before, except we're going to show you how this connection is made. Okay, so we're going to select the title, the artist ID, the artist's ID, and name. And so you can see how we're seeing the whole table. At this table, these things have been joined together, like there's glue in the middle between them. They've been glued together, and they're glued together in the situation where these two things match. So if you type that, that's what you see. And so that's a way, these don't really need to be shown, but they are the source of the connection. Okay? So that's the source of the connection, and by just selecting them, you can see what it looks like. Okay, so let's construct another one. Let's say we want the track's title and the genre's name. And if we take a look at the track, right, we've got genre ID. Now we have some replication here, and then we do need to do this lookup, right? And we want to see all the tracks, right? All the tracks along with their genres, right? Rock, rock, metal, metal. So now we've reconstituted the duplicates, right? This is what the user wants to see, but this is what we're storing in our database, right? So again, we say select track title, that's this thing. Genre name, that's that thing from a different table. From track join to genre, so that makes like this big blob thing that's a super row that smears across two tables. And then we have an on clause, and you think these are hard to construct, but oh, this is the track table, there's a foreign key name genre ID, oh, and that's going to be equal to table name.id, right? I almost cut and paste these things so fast as I write them, and so they get easier and easier and easier when going from the track table to the genre table, and the syntax that I use for the connection is very canonical. I do it over and over and over again. Okay, so let me run this guy, and there we go. We've reconstructed the replication. But this is also a good time to show you a little bit more about what's going on underneath this join, right? And now it seems all pretty and simple and this on clause. But what happens if we just take out the on clause? Select these two things from these guys glued together. Somehow we've glued these two tables together. So if you don't have an on clause, what happens is it basically says all combinations. All combinations. So there's 4 rows here and 2 rows here. So all combination of each row here, so this turns into 2, this turns into 2, this turns into 2, so that turns into 8. Now, if this had 100 and this had 100, that'd be 10,000. And so if you don't have an on clause, it ends up with all combinations. And we can show this. So this is exactly the same select statement. Track title, genre ID, genre ID. We're adding the middle, the joiner guys that would have been an on clause. And we're saying from track, join with genre, and no on clause. Okay, that's the thing that's changed. We added these 2 columns, and we took away the join clause. So let's take a look at what happens when we run this one. And lines don't matter, so the fact that I put this on multiple lines, you'll see it doesn't care. And so you can add spacing and lines to make your SQL look prettier. I do that all the time. I indent them. Indenting has no significance, but it is still very pretty. So now we see that we're getting all the combinations, right? 1, 1, 1, 2, 1, 1. So Black Dog has got both genres. So it got genre 1 and genre 2. Because we don't have an on clause, so it's not interested in matching. And so you can think of a join, as building across both tables all possible combinations between the tables. The on clause is throwing away the ones that don't match. Or a better way to say it is it's picking the ones that do match. Right? We like this combination, we like this combination, we like this combination, and we like this combination. That's what the on clause is doing, is it's picking the ones where there's a match. If you don't have the on clause, then boom, all combinations, 1 to 2. This is one row and it's being combined with that. This is the next row and we want both combinations. This is the third row, all combinations. 4th row, all combinations. And then the on clause wipes out the non-matching ones. Oops, I did it wrong again. Keep doing it wrong. But you get the idea. So that's the on clause. That's really how it works. And frankly, this is one of the things when I first looked at it, like, it must be doing that. But it doesn't do that. When it sees the on clause, it's really clever about pulling things in. Super clever. Again, that's not our problem. So now it can get complex. Because now what we want is the track title, the artist name, the album title, and the genre name. And this looks like a lot of stuff, but if you follow it, it's a pattern. So we have a select. These are the things we want. That is the list of the output we want. We're not interested in all the IDs. And we have to have this long from clause that says track, join with genre, join with album, join with artist. That's all the rows, all the tables concatenated together. And then the on clause, which seems kind of tricky, but now we start from track and work out that we have the foreign key in track of genre ID is equal to the genre's primary key, and the track's album ID is equal to the album's primary key, and there's one more foreign key, and that's the album's artist ID equals the artist ID. So go back to that little picture that we had this, that pointed to this, that pointed to that, that pointed to that. We just look at this, the picture, and this is why the pictures are so important, and we reconstruct all this. And so this, for me, it may look a little complex, but after you do it a few times, you realize that the naming convention really, really saves you. Okay? Let me show you that. Select this whole monstrous mess. Type her in, and then run it, and we've reconstructed it, right? Now we've got replication here, but that's the output. That's the beauty of databases. You reconstruct any replication, but you don't actually store the replication. And that's why you have to learn to write join clauses. So if we think about this, we've gone full circle. It's taken us, just like any startup, it just took us like 3 days to build our product. We started with a user interface that we designed that had replication. Then we came up with a logical data model, then a physical data model, then we inserted all the data, we connected things with numbers instead of strings, and now we use a join to reconstruct it. And so we start here, we go through a step, and then we come back to here, and we're able to reconstruct, in effect, the output that our end users are going to want to see, except now we can handle millions or billions of rows because we have carefully constructed a data model that makes sense.
Hello everybody, and welcome to Python for Everybody. We're going to do some code walkthroughs, actually running some code. If you want to follow along with the code, the sample code is here in the materials of my Python for Everybody website, so you can take a look at that. So the code we're going to look at is from the database chapter, and we're going to look at tracks.py. So a lot of the lectures that I give in this database chapter are just about SQL. And this is really about SQL and Python. So I'll go through this in some detail. So the code that I'm going through is in tracks. There's also tracks.zip that you can grab that has these two things. It's got this library.xml file which you can export from your, if you have iTunes, you can export this, or you can just play with my iTunes. And so this is also going to review how to read XML. So we're going to actually pull all this data. And this XML is that Apple produces out of iTunes is a little weird in that it's kind of key values, and so you see key value pairs, and it even uses the word dictionary. And so it's like, I'm going to make a dictionary that has this, then a dictionary within a dictionary. This to me would be so nice if it was JSON, because it's really a list of dictionaries. This is a dictionary, then another dictionary, then another dictionary, and then the key for that dictionary, and it's a weird format. But we'll write some Python to be able to read it. And so you export that from iTunes, and you can use my file or you can use your file. It might be more fun to use your file. So here's tracks.py. We're going to do some XML, and so we import that. We're going to import SQLite 3 because we want to talk to the database. And then we're going to make a database connection. And in this, once we run this, you'll see that that file will exist. And so right now, if I'm in my tracks data, that file doesn't exist. But what we'll see is this is going to actually create it. Now remember that we have a cursor, which is sort of like a file handle. It's really a database handle, as it were. And in order to sort of bootstrap this nicely, we are going, because this code is going to run all the time, it's going to run and read all of library.xml. In later things, we won't wipe out the database every time. And so I'm executing a script which is a series of SQL commands separated by semicolons. So I'm going to throw away the artist table, album table, and track table. very similar to the stuff we covered in lecture. And then I'm going to do the create table, and I'm doing this all automatically. And so, and you'll notice this is a triple quoted string, so this is just one big long string here, and it happens to know that it's SQL. I'll thank you, Adam, for that. And so it creates all these things. Now, it's not quite as rich as the data model we built because there's no genres in here. And so it's artist, album, track, and then there's a foreign key for album ID and a foreign key for artist ID, which it's sort of a subset of what we're doing. And so when that's done, that actually creates all the tables, and we'll see those in a moment once we run the code. Then it asks for a file name for the XML, right? And so that's what that is. And we're going to, I wrote a function that does a lookup that it's really weird because if you look at these files, like in this dictionary, there is a key, right? And so the key of this dictionary, this really should have been a key value pair. But so I had it. There's this weird thing where the key for an object is inside of the object, and so we're going to grab we're going to loop through all the children in this outer dictionary and find a child tag that has a particular key. And so you'll see how this works. And this was something I was going to use over and over again. And so the first thing we're going to do is we're going to just parse the string, and this is the string. And then this, of course, is an XML ET object. And then we're going to say, we're going to do a find all. And so this shows how the find all, we're going to go the third level dictionaries. We want to see all of the tracks. And so we have a dictionary and a dictionary and a dictionary. And so what we want is all of these guys, right? All those guys right there, right? Track ID. So we're going to get a list of all those. That'll be the first one. This will be the second one, because the find all says go to the find the dictionary key, then a dictionary key, a dictionary tag within that, and a dictionary tag. So and then we'll tell how many things we got, and then we're going to loop through. And entry is going to iterate through each of these, and see, we'll get our name and our artist. Another one bites the dust, a queen, and away we go. And then the next time through the loop, we'll hit this one. Okay, so then what we're going to do is we're going to go through all those entries, and if there's no track ID, and if that's this track ID field, where are you hiding? Track ID. If we don't have that, we're going to continue. And then we're going to look up the name, artist, album, play count, rating, and total time. Okay? And so here they are, play count. A lot of those things that we had in the sample lecture that I did. And we're going to look those things up, and we're going to do some sanity checking. If we didn't get a name or an artist or an album, we're going to continue. We're going to print them out, and then we are going to ask for remember how you have to get the primary key of a row so you can use it? So the way we're going to do this is we're going to do an insert or ignore. And so this or ignore basically says, because I said that the artist name, go up here, I said the artist name is unique, which means if I try to attempt to insert the same artist twice, it will blow up, okay, because I put this constraint on that, except when I say insert or ignore, that basically says, hey, if it's already there, don't insert it again. So what I'm doing here is insert or ignore into artist. So this is putting a new row into the artist table unless there's already a row in that artist table. And this syntax right here, the question mark is sort of the where this artist variable goes, and this is a tuple, but I have to sort of put this comma in to force it to be a tuple. So this is the way you have a one tuple. And then what I need to know is I need to know the primary key of this particular artist row. Now, this line may or may not have actually done the insert, and so I need to know what the ID for that particular artist is. So I do a select ID from artist where name equals. Now, it either was already there or I'm getting it fresh and brand new. So I do an artist ID equals, I fetch one row, and it's going to be the first thing, given that I only selected ID. And so this artist ID
is going to be the ID. Now I have the foreign key for the album title, right? And so now I'm going to insert into the title artist ID. This is the foreign key to the artist table. And I got this value that I just moments ago retrieved. And I got the album title. But this also is insert or ignore, because now if you look, I have unique on the album title. Yep, unique's on the album title. So that'll do nothing. It doesn't blow up. Or ignore says don't blow up, just do nothing, because this next line is going to select it. And I grab the album's foreign key for either the existing row or the new row, and then I'm going to insert or replace. And so what this basically says is if the unique constraint would be violated, this turns into an update. Now, not all SQLs have this, but SQLite has this that basically says insert or replace. Some SQLs are totally standard. Some things we do, like this select statement is a totally standard part of SQL. Then insert is totally standard, but insert or replace and insert or ignore is not totally standard. But that's okay. It works for SQLite, which is what we're doing. And so we have the title, album ID, length, rating, and count. And then we have a tuple that does all that stuff. And of course, the title is unique, right? The title is unique in the track table as well. And so we've inserted that. So the clever bit here is both dealing with new or existing names in these 3 lines. And we see that pattern twice here where we're doing that. Okay? So there's not much left to do except run this code. Hopefully it runs. Python 3 tracks.py and library.xml. Whoosh! Okay, so that is my so we found 404 of those dictionaries, 3D dictionaries, and now it's starting to insert them. And we can take a look at, so we can do an ls-l or dir on Windows, we'll see that we made a track database. We extracted the data from this library and we made a track database, and we have all these foreign keys. So let's go and take a look at the SQLite browser. File, open database, TrackDB SQLite, and come on up. Where'd you hide? I got it minimized, so there you go. Let's look at the database structure. We have an album, this is the structure, artist and track, we have no genre, and this is all like we did it by hand, except Python did all this work for us. If we take a look at the data and we start from the outside in, we have the artist names and their primary keys. Right, there's the artist names and primary keys. And then we have the albums and we have the artist IDs. See the artist IDs, how nice those are. So we have the primary key here and the foreign key there, and then we have the title. And if we get to the track, we have the album ID, and away we go. So if I was clever, I could be able to type some SQL. Oh, great. If I was smart, I'd have had this in a paste buffer. So, select track dot title album dot title artist dot name, I think. Artists has names and albums have titles. Yes. Okay, so I can do that from track join album. Album join. Let me make that a little bigger. Bring that over here. Album track join album join artist. Now I need an on clause, and I can say track dot album ID equals album. Notice how I know the name that I named these things, and album dot artist. This is so great when you use a naming convention artist ID. Golly, I think that might work. So let's just see what we get when we type that into the SQL box here. Execute SQL. Run. Yay, I got it right the first time. Right, so that's basically my nice little joined up track list. Oh, I'm so happy that I got that right the first time. Okay, well, you can play with this yourself. Play with this tracks, maybe make an export of your own iTunes library and run it with that. And so I hope that you found this particular bit of code useful. Okay? Cheers. So we've learned about foreign keys, we've learned about join, we've learned about how to normalize data to remove duplicates, but there's still one more basic data modeling thing that we have to learn about, and that is many-to-many relationships. And so everything we've done so far is what we call one-to-many, and that is an album has many tracks. So at the end of these arrows, and we see these on some of the crow's foot data model diagrams, one end is like many and then there's one. So one album and then many tracks. And so this is the kind of thing that we've got, and we've got a foreign key in the many side, so that allows there to be many tracks for one album, and then another album would have many tracks, right? And so that's the idea, is there's a set of tracks that have the same, I mean, this is the duplication that we just got rid of, and that's called a many-to-one or a one-to-many, okay? And so that is one form, and it's the most common form. And, you know, we see this in our tables where we have, you know, genre ID or album ID, and we have duplication in here. And this is the many side, so there's many of these things for one of those things. And as an example of biological mother and children, single biological mother might have many children. And this is also a crow's foot diagram, and this little, like, crow's foot says many, and then one shows right there. So when we're drawing these data model diagrams, which we haven't spent too much time with, we always draw them in a way so that we capture the manyness or the cardinality of each end of the relationship. Now, so that's one-to-many. But sometimes we have a relationship between data that's many-to-many. And frankly, in our music data that we've been playing with, I already told you that, like, well, there's actually many artists on an album. And they're like, but I said, don't worry about that. Well, now we're going to worry about that. So the example that I took from Wikipedia is books and authors. There are many authors and many books. And so, you know, one author may talk to many books, and one book may have different authors that they're connected to. And so we can't say that either of these is a one relationship. And so we call this a many-to-many. On both ends, there's a many-to-many. But in terms of the table that we want to do, there is no way, you can't put a single foreign key in this side. Oops, come back. We can't put a foreign key in this table to point to books, and we can't put a foreign key in books pointing to authors, because that would be sort of a one on either side. And so we build a table in the middle, okay? And in Wikipedia they call it a junction table, all kinds of names for this thing. But what we do is we have a little table that we create. We still have a books table and an authors table, but then we have a table that models nothing but the connection between them. And so we decompose this many-to-many relationship into a many-to-one relationship and a many-to-one relationship. And these two things then we can model properly using the exact same techniques that we've been using all along. And so we end up with a table that has two foreign keys in it and no primary key. So let's take a look at how this looks when we actually build it and model it. So here we're going to have something that I care a lot about, courses and users. So this has to do with the fact that one user is a member of many courses, and each course has a member of many users. And so the relationship between courses and users, the member of relationship, is many on both ends. And we just can't model that directly, so we make a little mini table in the middle, right? So we have called this the membership table, or a table called member. We still have a user table and a course table, and we have a primary key in the course and the user table. And what we do is we have this member table that has each row has 2 foreign keys. And it is a connection, so think of all the courses on one side and all the users on another side. Each connection, these could be friends of people, each connection has one row that connects a particular course with a particular user. And that's how it works. And so then that decomposes our many-to-many relationship into 2 halves of 2 many-to-ones that then models the many-to-many relationship between the 2 tables. We don't put an ID, we don't put that in there because we can make a composite key, which is both these 2 things are the primary key for that table. They're both numbers, duplication is allowed, and so this is all perfectly great. Now sometimes we'll model something like put a role here, so that you can say, okay, this is courses and users. We might indicate that this particular user-course combination also is an instructor, and this particular is a student, right? And so we can sometimes put a little bit of extra data on the link itself, and so we have a little bit of data that we add down there. Okay? So we make this little table in the middle. And so here we're going to run some databases. I'm going to start with a fresh database. I'm going to make a user table. The main difference is I'm going to give the primary key for the users. I'm going to make a course table, and this is our standard primary key stuff. I'm going to have a name and email for the users and a title for the courses. And then, those are just normal things that we're used to doing, but now what we're going to do is create this little connector table that's going to have it's going to have a role ID and a course ID, a user ID and a course ID, and then we're going to model a little bit of data right here in the middle, and we're going to model role. And this is going to allow us to say whether someone's a teacher or a student. And the other thing that we're doing that's effectively a substitute for this primary key is we're saying our primary key is actually 2 columns together, and it's the combination. So this forces it to be unique, but it's really the combination of user ID and course ID must be unique. Okay? So let's take a look at this. Let's actually go ahead and run some code. And so what I'm going to suggest that you do is to start with a brand new fresh database. Just click New Database, right? And we're going to call this, I'll call it SQL3 New Database. And I'm not going to do my table there. I'm going to go over to the Execute SQL, which by now I hope is becoming somewhat comfortable to you. And then I am going to grab, actually I'm going to grab these 2. First we'll grab those 2 create table statements. I'll put a semicolon at the end of this one so we can run them both. Let's see if they worked. Yep, I've got a course and a user, primary key, title, ID, name, just exactly what we've got. And so now what we're going to do is we are going to execute the SQL to make the little connector table. So I'll paste that in, and I will run that. See if it worked, and it did work. So we're all good, primary key, and now we're going to put some data in. So let's take a look at some data. When we're done, we've got that, which we've seen. And so we're going to insert some users and some courses. So let's take a look at that before we go doing it. So because these have auto-increment primary keys, we're just going to insert the name and the email, jane@tsugi.org, and we're going to insert 3 users, and then we're going to get the user IDs, and then we're going to insert 3 courses, Python, SQL, and PHP. And so we'll just do those. Those are nothing special. They're no different than the things we've been doing all along. Go over here in SQL. They all have semicolons at the end. So it all ran. So we'll browse the data. We see the course data, and we see the user data, and there's nothing in the membership data. I mean, it does. The database doesn't know that we've done anything like this. We just inserted some stuff over here. And what we're really doing is establishing the primary key in this ID column. So Python is 1, SQL is 2, and PHP is 3. And so now we're going to actually put some data into the member column. And the user ID, course ID, role. So we're connecting one user to one course and then assigning a role to that particular membership. So this is a membership record, who is a member of what, and some aspect of it. And there can be a few things that are often a few more columns that you can do. So let's take a look at the thing we've got to do to actually insert users into the courses, right? So here's the numbers that we've got. And so now what we're going to do is insert into, there we go, insert into the member table the enrollment records, as it were. So we've got to insert user ID, course ID, foreign keys, and then the role. And so this says we're going to do user 1 is going to be in course 1, and we'll make 1 be the instructor. Okay? And then we're saying user 2 is in course 1 as a student, user 3 is in course 1 as a student, user 1 is in course 2 as a student, user 2 is in course 2 as an instructor, etc., etc., etc. And so because we know what these numbers are in actual code, we'll know what the numbers are. We know what the numbers are, and so we sort of put them right in the insert statements, and that's how we make our connections. So let's go ahead and run those. Go to SQL and insert all those. Click. Oh, yikes. Hope I didn't do that twice. Nope, I didn't do it twice. I'm glad. Let me just refresh to make sure I didn't do it twice. Okay, so that's just the numbers that came from those insert statements, and instructor, 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 the courses, and the students. Okay, and so now what we have is we have in our database, we have now connected these things together, right? So we've got them all connected together. We've got our user table, we've got our course table, and then we've got our connectors that go from here to here and here to here. And we are modeling a little tiny bit of data on the connection. That's what we call that, on the connection. Okay? So let's get some data out of this table now. We are going to write a select statement, select username, member role, and then course title. I'm going to select those from the user joined with the member joined with the course. So we're going to join all those together into one big long row, long row. We use the on clause, and the member user ID is equal to the user's ID, and the members and the courses, the membership course ID is equal to the course's ID. Membership course ID equals the course's ID. Oh, and then we're going to do cool stuff. We're going to order by the course title, then the member role, the way these, and then member role descending, and then the username. So what this means is the precedence is course title is the most important thing, the role is the next most important thing, and we're going to do that descending, and then the username is the third most important thing. So this is going to give us sorted by course first, and then within course it's role first, and then for people that have the same role, like this one has the same role. So this allows us to see the teachers first and then the students in alphabetical order, because the role is 1 for teachers and 0 for students. Okay, so that's what we get when we make this join. And so we've kind of created an enrollment record. If we had a where clause, we could pick it for one particular course, etc., etc. So let's go ahead and run that select. It will be really boring if everything went well. Execute SQL, paste that SQL in, and run that SQL. And so we see ordered by course, then ordered by role, and then within the same role, it's ordered by student name. Okay, so that was an example of 3 things in the order by clause. Okay, so you see this sort of working. If you look at various data models, this happens to be a data model for your auto grader, actually. It uses a piece of software called Sugi, and the interaction between the learning system and Sugi has to model things like what course you're coming from, the membership you are, whether you're a teacher or not, And so if I look at this, not that you really need to look at this in great detail, we got this is a production software, a user table, a context, which is the same as course, and then the membership. And the membership has a many to one. So we have a many-to-many relationship between users and courses, but we model it with this little table that's the connector table. And there's a role in there. As you might expect in any teaching and learning environment, you're going to keep track of the role. And I have a thing called the role override, and I also have two little things that keep track of when things happen. And so let's see. So some of these things, so that's a many-to-many relationship. Most of these other things are many-to-one. This is a many-to-one relationship. And so this is a modified crow's foot. This is a many-to-one relationship between the course link. This happens to be the link that you click on, blah, 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 blah. And this is actually your grade, and results are grade. And so there's many results for one link, and that's because every student gets their own grade. Okay, so this just happens to be the data model for this piece of software that you have now been using perhaps for several months. But you see one of these many-to-many relationships. Okay, so why did we do all this? Why did we do all of these things? Why did we make these little integers? Why did we teach you about join? Why did we teach about many-to-many? Why did we make your data look so crazy? And that is all about speed. And you might say, I don't care about speed. And it turns out that there are plenty of programs for which you don't care about speed. You know, the little program to calculate the U.S. floor from the Europe floor, it doesn't matter. Reading 10,000 lines from a file doesn't matter. But when you build, say, an online application or even a large data analysis application, speed begins to matter. And so what happens is you cross over this moment where it becomes too slow, and then the only way to make it go fast is to really make it go fast. And so when you use databases, you can do things that seem amazingly fast. And so all this normalization, the amount of data that you store, the amount of data you scan, is really taken out. And it's not really a trade-off. Either your thing is small enough that you don't have to do this, or you cross over this point where your application will fail unless you don't do this. And so that's why this is an important skill to have. And so we've covered a lot of SQL in a short period of time. There's much more to learn. People always ask me, is there an advanced SQL class? And I'm like, well, there's kind of a beginning SQL class and then the rest of your life. Because you can always learn more about structured query language and how databases work and what goes fast and what doesn't go fast. A couple things that you can look for as topics that we really didn't cover very well. Indexes, this has to do with like logical keys and lookups really fast for strings. Constraints, we did have a thing not null. But there's other constraints that you can put on data. And transactions, they're a way to group operations like if a read starts, no more reads can happen until a write happens. And so it's a way of blocking things. And so these are all very, very important topics. And so this is relational databases could be a profession all by itself. Just knowing how to do databases is impressive. Doing database design is impressive. And I hope this has got you to the point where you can somewhat understand what's going on and then learn the rest of your life. Okay? See you.
Hello and welcome to our code walkthrough on the roster code. So the learning objective of this is to do a many-to-many table. And so the idea is that we're going to, just like we talked about in lecture, we're going to have a set of users, we're going to have a set of courses, and then we're going to have a connector table or a many-to-many table that basically has two foreign keys. So we are going to use the integer not null primary key auto increment unique as the way to get auto assignment of the primary keys in the user table and the course table. And then we're going to say that the name, which is like a logical key, and then the course title, we're going to mark those as unique. And we're going to take advantage of that in a moment. And so you'll see how we take advantage of that. So what unique means is if you try to insert the same string into this column, like Chuck twice, then it's going to fail the second time because it's going to refuse to create a new record. And so if we just kind of like take a look, we're going to get our roster data from this sample JSON, which is just an array of arrays. And this is
the person's name, the class that they're in, and whether they are a teacher or a student. And so we're going to read that. So we need the JSON library and the SQLite library. We make a database connection and we get a cursor. The cursor is the kind of more like the file handle. You send SQL commands to the cursor and then you read the cursor to get the data back. The connection can create more than one cursor so you can have more than one set of commands. But the cursor is generally like the file handle to the database server. And we are going to execute a big script, and you'll notice this is a triple quoted string that goes all the way down to here. And so some people would just give this to you in a text file and have you cut and paste this and then go run that in your SQLite browser to create them. But that's okay, because what we're going to do is we're going to set this up. It will either reconnect to existing file name rosterdb.sqlite, and if I look where I'm at, I do an ls, we find that that file is not there. So the first time I run it, it's going to create it. But I want this to start fresh every time, so I'm going to wipe out the tables if they exist. That way you can run it over and over and over again in case you make a mistake here. Now I don't have a mistake, or hopefully I don't have a mistake on this. So we're going to drop 3 tables, and we're going to create 3 tables. And here we're going to create the table that has 2 foreign keys, user ID, course ID, that are sort of going outwards from the member table. And then we're going to model a little bit of the data at the role. And again, this is straight from the lecture. And the primary key is actually a composite primary key, because we're going to look up, and it's going to force this to be the combination of user ID and course ID to be unique. But there can be many user IDs and many course IDs, but only one particular combination of a value for user ID and course ID. And so that's what we're basically saying. You can be a member of a course, but you can only do that once. You can't be like a member of the course a bunch of times. So we're going to, that should be roster data sample. That's okay to, fix a bug. Save that, roster data sample. And so that's just this file, and it's really just an array, and then each row is an array, and it's a way for us to get this roster data in. And so once we do load S on JSON, we're parsing it, and then this is going to be an array of arrays. And so for entry in JSON data, so entry is going to be one of these things. So entry itself is a row. So an entry sub 0 is the name, and entry sub 1 is the title. Name, that's the sub 0, and that's the sub 1 of the particular entry that we're looking at. And we're going to print it out just for yucks as a tuple. So we make, that's what the 2 parentheses are. This inner thing is a 2 tuple. And we're then going to take the person, and we're going to do an insert, and this is new, or ignore. So what the or ignore means is if this insert would cause an error, please don't blow up. Don't just ignore that I tried to insert it. And so this is our trick, and it's a beautiful trick. It's like a gorgeously beautiful trick here. If we insert the name Chuck twice, or ignore will just mean that nothing happens, meaning it's already there. Okay, so if it's already there. If it's not there, it'll put it in. And the unique will guarantee that it only goes in once. So we just, in effect, always attempt to insert it. And if it's been there once, then it's all set. And so this insert or ignore is a super powerful mechanism. I use it all the time. And we have a placeholder in the form of a question mark. And then we have, so one of these days we'll have 2 things that we're asking for. As a matter of fact, here it is. There's a tuple down here. But this is kind of a tuple with 1 item in it, name. And that name is then going to substitute in for there without, while avoiding SQL injection. So this runs. It may or may not insert a new record, but if this Chuck or whomever the name is not there, it will give us a new record. And then we are going to get back the ID. And so this is the logical key, and this is the primary key. And that primary key is going to be auto constructed for us, and so we need to know what it is. So we say select ID from user where name equals, and then that same name. So that's Chuck, and so that gives us one. And then what we do
is we're going to fetch one record from the cursor, because that's a select and it gives us back a cursor. There's only hopefully one record there because it's unique. I could put a limit 1 in there, but that'd be kind of redundant because the name is a unique key. And then the sub-0 just means if there were more than one thing that I was selecting, which we'll see in a bit, the sub-0 is just the first thing. And so this is going to give us the integer user ID that was assigned, or if we're coming through later for Chuck, Charlie later, that will be the old one. So this is inserted if it doesn't exist, and this is get the newly created ID field or the original ID field. And so part of this works by having both a logical key and a primary key. The primary key is auto-generated, but the name is a logical key and it's unique, and so that's our trick to get that assigned thing. Before, we just looked at it in the user interface of SQLite browser and wrote it down, but this is how we do it in code. So we need to know what that key is, whether it was new or not. And then we do the exact same pattern for the course, except we're inserting the course title, so that's no big deal. And so we're going to get the user ID, course ID, and then what we're going to do is we are going to insert or replace. So this is it. Basically, remember that this user ID course ID combination is the primary key for this member table. If there is a duplicate, if this combination is already there, this becomes effectively an update statement. And we have these two number values. Now what's missing here is the role is not there. And so user ID, course ID, this is the SQL bit. And now we have a tuple with 2 items in it. And that's because we have 2 question marks. And then we commit it. And as I mentioned before, sometimes you want to commit every time through. The commit it turns out that these things are less costly, but that's because it's not always writing all the way to disk. Whereas when you enter the commit, it's going to go and write everything to disk, pause until it's complete, and then your program doesn't continue. So sometimes we don't run this every single time through. Okay, so let's just go ahead and run this. The only thing we're going to see is the output of the name and the title as it's running. So if I do Python 3 roster.py, hopefully I can hit enter. So you'll notice, by the way, that this SQLite now exists, right? And it has no data in it. So let me see if I can open this database and see it. So you see that there's no data. So we're the code, we've run this code in effect up to this point. So we've done all the create tables and all that stuff. And so the create tables are there. So all this data is here. It did it. We haven't started putting any data into it yet, because if we look at browse data, we're not finding anything in here. Okay? There's no data to browse. Now, hopefully we won't have locked ourselves, because we are sitting right here, and when I hit enter over here, then it's going to go, it's just going to run really fast. So I'll hit enter, it'll read it, and so it inserted all of those things, and now it's been changed. And if I hit refresh over here, we will see in the user it just sort of assigned user IDs, right? The columns auto-assigned. We will find in the course that those courses are all auto-assigned. There's the courses. And there's no duplicates because this is unique, right? And so these are the newly created things. But then membership is user ID, course ID. And so again, the primary key, as it were, the unique constraint / primary key is the combination of these things. And I haven't put anything in role. And so if you scroll through these, you see all of the users who are members of the courses that they're part of. Okay? So there you go. And I'll leave it up to you to come up with the join. I'll leave it up to you to figure out how to put the role in, but I just wanted to kind of give you a bit of a walkthrough of this code base, and in particular, the tricks of the uniqueness keys, the auto increment keys, the logical key uniqueness, and then this kind of composite primary key, and then the trick of insert or ignore, and then the quick select that comes right afterwards to get the newly generated ID or to get the old ID. You can insert or sort, and then insert or replace, which is a combination of a insert and an update. So I hope you found this this example useful and can apply it and basically create many-to-many tables.
We were an early adopter of version 6 Unix here, and we had a VAX and PDP-11s and all that stuff. And so we were happy to run Unix, and I was teaching a course on operating systems using version 6 Unix, and John Lyons of Australia wrote a little book sort of describing it line by line, and it was very popular at universities. And the bean counters at AT&T decided this was a bad idea. That, you know, having every student in the world learn about their product, which they owned, they thought was a horrible idea. So with version 7 came with a license saying, thou shalt not teach. Okay, so the version 7 license said you couldn't teach version 7 Unix anymore, which is, it's got to be up there, ranking up there, or something Xerox did as, the dumbest mistake in all of history. But they did that. So we couldn't teach Unix anymore. I said, maybe I'll write my own operating system, which is compatible with V7, and then I can teach it. I sat down and I began writing, and now it sort of worked. I got it almost to the point where it worked. And it was crashing at random, but it was all the functionality was there, and it would run for 15 minutes, and then it would crash. And I was like about to give up. I just couldn't. So I said, I'll write a simulator for the PC, and I'll run on the simulator because that's entirely deterministic and reproducible. And then after it crashes, I can go run it again and print out the last 100,000 instructions, find out what happened. So I wrote the simulator. It took me a little while, but I got it running. So I had a complete simulator for the PC. If I had been smart, I would have invented VMware. This is, in the 80s, because I already, I'd done basically the work. I could have done translation instead of interpretation, but I didn't think it was, So I wrote a PC simulator. Anybody could do that. So I didn't care. So it worked perfectly on the simulator. It would run forever. It wouldn't run on the hardware. It only ran on the simulator. And I'm kind of scratching my head from, gee, how come? One of my students, Robert from NASA, mentioned me I was explaining this problem to him, mentioned me offhand, when the Intel chip gets hot, it gives interrupt 15. And I said, no, it doesn't. He said, yeah, I heard that somewhere. I said, the manual doesn't mention anything about that. And so I said, well, I don't know. I can put in a test. I wasn't catching interrupt 15, of course, because the manual didn't mention it existed. So I put in a little piece of code which caught interrupt 15. And sure enough, within an hour of running it, I get this message, hi, I'm interrupt 15. This is impossible. You'll never see this message. So I was saying all these very unpleasant things which I cannot repeat about the internet, about Intel. If they want to put a thermal sensor, great. Please put it in the manual, though. Mention it. So I put it in, and all of a sudden Minix worked. Okay. If Robert hadn't made that comment, there would have been no Minix. If there were no Minix, there'd be no Linux, because Linus went out and bought a PC specifically for the purpose of running Minix. He was in the Minix news group. We had a big news group on Usenet news groups. He spent a lot of time developing Linux based on Minix. He changed this, he changed that, and eventually it changed almost everything. And so it sort of launched as its own system. So if Robert hadn't made that comment, there would have been no Minix, there would have been no Linux. If there had been no Linux, there would have been no Android, because the Android is Linux. Okay? And if there had been no Android, the relative stock prices of Samsung and Apple would have been quite different, because the Apple is based on iOS, which is FreeBSD, which came from a whole different strain of Unix. So that wouldn't have been affected by the presence or absence of Linux. But Robert's remark ultimately changed billions of dollars of valuation in the Samsung versus Apple stock prices. And if he hadn't made that, the world would be quite different. There probably wouldn't have been an Android. And heaven knows what all the other things that depend on Linux and Android.
The server bits of all of that.
All the server parts of it. They might have been using FreeBSD or something instead. Who knows? But the world. That one little offhand remark. Had all these consequences downstream.
So then how did
anyway,
you write Minix, then write the book?
Yeah, I wrote Minix, and then I wanted to document it, because I wanted something like Lyon's book, which explained in a course. So the book, most of the chapters have 3 sections. One is sort of the general principles of file systems or process managers and whatever. The second part is how these general principles apply to Minix. What is the memory management algorithm, and how is the file system organized, and what are the key data structures, and so on. And the third part of every chapter is, now we're going to look at the code. Here on line 10,720, we see the main headers for the file system. And here we're declaring these headers, and now on line 14,000, we're starting with the actual main loop of the file system, and it goes and gets a request, and it takes it apart. There's a switch statement, it figures out what to do, and so it goes through the code bit by bit. So it was like Lyon's code, and the book came with a bunch of floppy disks, which was the only transport medium in those days, where you actually had the source code. And so the book came out. It was an enormous success. And at the same time, there was already BSD, which was a mature, stable working system which had 20 years of background, the VAX and the PDP-11. And the guys who formed it, McCusick and so on, they formed a company, BSD Incorporated, and they were trying to sell it commercially. and their phone number was 1-800-ITS-UNIX. And so what does AT&T do? Again, in one of the more brilliant commercial moves in all of history, they sued BSDI to get rid of them. And they had no knowledge at all how to sell Unix. If anybody there had an IQ of above about, say 2-digit numbers, they would have gone to the BSDI guys and say, we want to buy your company, how much? And given you're AT&T, the biggest corporation in the world, no matter what number they had mentioned, we would have said, good, sign here, and they would have had the BSDI guys sell Unix. There would have been no MS-DOS, there would have been no Windows, it would have been all Unix, and they try to stop these guys. So BSD was blocked from going commercial. I knew about this, and so I didn't want to make Minix like big commercial things. So I figured the BSD guys eventually are going to go out there, and that's a stable, mature system with many programmers and many users, many all software. That would take over the commercial aspect of this free software world. But it didn't because of the stupid lawsuit from AT&T. And so that was the interval that Linux got a chance to grow. So one of those freaky, I said that the bean counter at AT&T who sued these guys instead of buying the company and saying, you're our marketing division, go sell it.
But at the same time, if you think about Minix, it let the Linux movement let Minix stay for teaching and education.
For a while, yeah. We've changed that recently.
Okay.
I got one of these, the European Union, they decided to set up a couple of new programs where basically they would, give a large chunk of money, about €2.5 million, which is, I don't know, $3.5 or $4 million, to one specific investigator. There's two categories: young investigators who are just sort of getting started, and senior ones who have a track record, and basically let them go do their thing. And I applied for this, and I got one of them. And with this ERC Advanced grant, we're trying to go commercial, with Minix. We're pushing it in the area of embedded systems and high reliability, because it's got a kernel and all these servers that run separately in user spaces, user mode processes. And in particular, if one of them crashes, there's a reasonable chance we can repair it on the fly without disturbing running programs. And so if the disk driver fails, we can detect that. We can start up another disk driver, and there's a glitch of a couple hundred milliseconds while we're restarting things, but things go on. If the disk driver in Linux crashes, that's the end of Linux. Okay, you have to reboot the whole computer. So we think there might be a little niche in there.
I think there's a significant niche, actually. I think that the problem with modern operating systems is they're getting too large and too complex.
Yeah, and this breaks up into little pieces. And another thing which we can do now, and just before we started, one of my PhD students came in. He's working on live update, so we can update almost all of the operating system on the fly from version 3.3 to version 3.4, which might have thousands of changes, including data structures, on the fly while the system is running, while application programs are running, without changing or stopping or interfering with the running programs. And this is, tricky. The model, of course, is that the person who wrote version 3.4 was keenly aware of all the details of 3.3. So if there was some internal table, let's say the mount table, which was simply a linear list in 3.3, and he decided to make it a hash table in 3.4 because you could have a lot of things mounted, then he'd have to write the code for converting the one data structure to the other. So but basically you say I want to do an update, and there's a manager which handles that, and the manager goes to the old one and says, okay, finish off what you're doing now, don't take on any more new work, sort of queue it, and then when you're all done, let me know. And when it's done, then the manager starts up the new one, and the new one then goes to the old one and says, okay, I need all your data structures. And the LLVM compiler allows us to record in memory all the data structures very nicely, their types and locations. So it says to them, give me your first data structure. And then it gets the first data structure, sees if it's identical to the old one. If so, just copies it. If not, it's got to run a routine to do a conversion from, say, a linear table to a hash table or a list or whatever the new one is, and runs that. When it's all done, the whole thing is converted. Okay, it doesn't take very long. Computers are good at that. And then when it's all finished, he tells the manager, okay, I'm ready to go live. The manager then changes all the internal connections to point to the new one, makes the new one go live, kills off the old one, and there you go. And there's a slight glitch of maybe a couple hundred milliseconds for the application when there was no file service, but they don't know that unless you're doing hard real time. Everything works. And we think that might be interesting for applications that never want to go down. And they know that software has changed all the time. There are security fixes. And we're focusing this on the embedded world, where I think there's a lot of interest in keeping the thing running all the time. If you're running some real-time system, whether it's a radio telescope or electric power plant or some other real-time thing, you may not want to go down for reboots once in a while. And so a system which can could update itself, which can repair itself, which can try to have a fairly high availability, might have a niche in there. We've got it working in the lab now for the Beagle board, for the Beagle Bone. We're about to release it for the Beagle Black also, which is it's like the Raspberry Pi, but even better. So we're sort of trying to see if we can find a niche there.
Welcome to Chapter 15. We're going to have a little bit of a different take on Chapter 15. We're actually going to make more complex programs, and we're going to actually do multi-step programs in this chapter, and we're really just applying all of the skills that we've applied, that gained in the first chapters. And if you don't understand this material, you really need to go back and review all those other chapters, because we're going to start moving pretty fast. So what we're really going to work on is we're going to combine the act of working across the networks, and we wrote a program that read some stuff off the network. We've done that. We've looked at databases and how in Python programs can put stuff in databases. But now what we're going to do is we're going to use a database as an intermediate step. And we're going to be gathering from some kind of a data source. Increasingly, data is found on the web. Often you find it in the wild, and you're doing something pulling something from a Twitter API like we did in the previous, or a GeoJSON API, but then there's some rules about it. You might have to have an API key, or you might have a rate limit, or it might even be unreliable. And so you have this gathering process that basically says, look, this is slow, yucky, unreliable, dangerous, and you might want to start this up and then restart it. This is a hard process. This might take hours of time. It might even take days. And it might break, and it might get fixed, right? It might break and get fixed. And so this gathering process is something we want to be real careful, and that's why we tend to put the data in a database, because databases are really good at sort of not losing data, and you're halfway through and something blows up, the data you have is in the database. And so the gathering, in many ways, it'll be like, okay, how much data do I have? Now I'm going to go get some more data, put this in the database. Oh, we blew up, so now we're going to run again. We're going to start up again. And okay, start it up. Let's look at how much we got. We got more now. We're going to start at a different place looking at the data, and we're going to gather that and add it on in the database. And we might have to do this many, many times. As I mentioned in the GeoJSON thing, because there's only 2,500, it took me several days to get through 10,000 bits of data from the GeoData API. And what we tend to do is, in this gathering process, we tend not to do any analysis of the data. We're just like, we keep these programs relatively simple. They read something, they stick it in the database, read it, stick it in the database, deal with the fact that you've been blown up and have to start halfway through. So we keep these really very simple. And then we get our data. And in here, sometimes we'll have very raw data, because we're really focusing this database on handling the complex management of the problems that you have while you're gathering the data. So at some point, you've got your raw data. And you may have a separate step that is a Python program that goes through and reads all the data in this database, runs a Python program, and might even run another database. And frankly, you could have more databases here, etc. But some process that basically reads the raw data. And then you might write another database. Some of these will just actually go straight to analysis or visualization in our earlier ones. But in later, what we'll do is have this pretty data. This is the clean data. This is the data that makes sense, right? It's the clean data. Then we're going to write another. So each one of these is a Python program, and now we're going to run maybe a couple other Python programs. This is going to read from the clean database and do some analysis and print us out some data, or we might read from the clean database and then try to visualize the results. And so these are separate steps, and each of these boxes is a separate Python program. Now, in a way, everything we've done up to this point has been write one Python program to produce some result, right? And we write a loop and we read the stuff and we make an array and then we print the array out. But in this, because the problem is harder to solve and there's unreliability and other external things, we will basically break it into multiple steps. And we'll write a little Python program for each of these steps. Now what we're working on is not exactly data mining. It is and it isn't. I don't call this data mining because that would be overstating what we're doing. There are many very complex data mining technologies, and that's not what we're going to cover in this course. There are other places that you can learn about data mining, and I like to think that our course that we're doing here is a good preparation for data mining, learning about data mining technology. And so there's open source things like Hadoop and Spark. Amazon has a whole data mining operation called Redshift, and there's many community source, and then ... And so don't assume that this is all there is to data mining. This is a particular style of data mining that I call personal data mining, right? And it is not to say that once you're done with this, you're a data mining expert, because that would be a gross overstatement. We're really more interested in this chapter on making you better Python programmers by solving some simple rudimentary data mining problems with Python programs, and then looking at those Python programs and becoming better Python programmers. So the first thing that we're going to do is we're going to build on something that we did in the last chapter, and that is talk to Google's geocoding API and pull some data into a database and then visualize something out of that database. And we're going to use the Google Maps API, so you do need to be connected to the internet when you do this. And so here we go. And of course, whenever you're doing any of these things, I will generally give you URLs to use other than the official URLs. You can use the official URLs, but at some point, we don't want them to get annoyed with so many students taking the class and pounding all of these APIs. I'll get some kind of an email that says, quit talking about our API. So I will, whenever possible, give you my own API to use for these kinds of things. And I'll give you a whole video showing you these programs in action. But right now, I just want to show you the general outline of the picture of how these things work. And so we do have the Google Geodata API here. We have played with this before. And so if you look at this program, geoload.py, by the way, you download all this stuff from right there, and these are just files in there. Geoload.py is a lot like the thing that you read before, that reads some JSON, hits a URL, reads some JSON, parses some JSON, and then writes the JSON into a database, right? And this actually takes as a list of locations. So if you remember the other thing, SU for each location, this actually takes where.data, which is a list of locations. And this can have thousands or even hundreds of thousands of locations. And then as we retrieve each location, we put lines in our database. And this ends up in a file called geodata.sqlite. .sqlite is the suffix for SQL data. And so this will run, and this can start and stop and start and stop. And remember, this is only 2,500 of these per day, start and stop, and slowly but surely we build this up. Now the interesting thing is, even if you haven't got all the data, you can still run these other things, because let's say you've got the first 500 of these records. Well, you can still make a pretty picture of 500 records, and then later the next day you can then go get 500 more or 1,000 more, depending on your network connection, et cetera, et cetera. And also, don't get yourself in trouble with your network service provider. They're running these things 24 hours a day and downloading gigabytes of data, and all of a sudden you're on some mobile device, and so just be careful how much data that you download. So at some point you have the data cached. We use the word cache, which is kind of a local copy of something that's elsewhere. So we've got a nice copy. And so now we don't need to talk to Google anymore. We've got all of our data sitting in this database. So we will write a little program called geodump.py. And it will write a loop that's going to loop through all the records in this database, loop, 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 loop. And this one prints it out just on the screen. And it tells you, oh yeah, and I also wrote as a side effect a bunch of the data into a file called where.js. This is a JavaScript file. And you can take a look at it. This is not a JavaScript class. And what I've given you is I've given you a whole bunch of HTML and JavaScript that takes care of all this. And this HTML file reads this JavaScript file and then calls the Google API to make all the little dots on the map for you, right? And so if you, in effect, pull more data in and then run this program and then run the program and then hit refresh on this screen, little dots will start popping up, okay? Now, the screen doesn't actually go straight to the database. You have to run the geodump.py. But now we're kind of seeing this multi-step process where you do this for a while, you get your data filled up, and then you're like, oh, I've got myself some nice raw data here that's been cached, and now I'm going to run it, see what's going on, and then I'll visualize it, okay? Now, like I said, I'm not going to teach you in this class exactly how to write each one of these things, although in the capstone, some of you may play around a bit with doing those kinds of things. So this is the summary of our first of 3 examples of how we're going to do this personal data mining. So we'll see you in the next one where we'll talk about PageRank algorithm.
So now in this last chapter, we're going to talk a little bit about visualizing data. But what we're really doing is we're sort of summing everything up, because we're going to retrieve data from the network, we're going to process the data, we're going to store it in a database, we're going to then write it out and visualize it. So it's all coming together. And it turns out that this notion of gathering data, the data gathering using the network, it's a pretty common thing. We might take a cleaning or processing step where the part of the problem is when you're pulling data off the net, you want to be able to start this process, because it'll run and run and run, and then your computer will crash or it'll go to sleep or something. And so you don't want to start from the beginning, because it might be quite a bit of data and it takes a while to do it. Or as we've seen in some, you might be talking to an API that's got some rate limit that says, oh, you just have to stop at 14 of these things or stop at 200 or whatever. So this is often a restartable process. And it's usually a simple process. It's usually a relatively small amount of code where you have a queue of things you want to retrieve. You go to the next one, and then you store it in database. Next one, store it in database. And when you start the process up, you start filling this database up with stuff. And then if it blows up and you restart it, the first thing it does is it reads the database, says, oh, I don't need any of those. And then it starts to get the next one and the next one and the next one and the next one. And that is how you make this restartable. And databases are really good at having it so that your program that's writing to the database can blow up and you don't corrupt your data. You don't have partial data. It's either written or it's not written. And so these things can blow up. And sometimes you just blow them up because you want to blow them up and start them up. And so they you start them up again. They scan down and say, where was I? Oh, I'll start here, 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 here. And so this is often a slow and restartable process. And it also might be limited, but for some reason. And so this runs for a while. And the third thing we'll do in this chapter, it might run for days actually. And then you have your data, and then you start doing stuff inside your computer where you don't really care so much about the network. Maybe this is raw data that came in off the APIs, and you want to make the data in some new little format. So you might go from one database to another database, or a database to a file, and kind of produce data that's really ready for visualization. If this might be a little complex, or there might be flaws in it, you might write scanners that go like, oh, wait a sec, this is inconsistent. Sometimes it looks like this and sometimes it looks like that. So I'll clean that stuff up. And then using some visualization or doing some Python programs that loop through the data once it's cleaned up, and then do some kind of summing or adding, or who knows what they are that they're doing, but analyzing or visualizing. And what we're going to use is we're going to use things like Google Maps to do our visualization, a lot of JavaScript, and a thing called d3.js, which is a JavaScript library. Now, in this class, we're not teaching you JavaScript, not going to teach you Google Maps. I provided all these things so that when you run these programs, that stuff is all there. But if you want to learn and see some examples of how to make a little simple JavaScript visualization with a line or a word cloud or a map, we've got it, and you can take a look at those things. Now, this is one form of data mining. And it's really kind of a data mining for an individual where you're pulling this data, you're getting it local, and then you're working with it. There are other much more sophisticated data mining technologies that you might find yourself using, but often what you'll also find is Python is part of these, or Python helps you manage these, or you write a Python program to scan through these things, or to prepare them, or to do something. And so there's lots of different data mining technologies. This is just one oversimplified, very Python-oriented data mining technology. I'd call this sort of personal data mining. And you should take classes if you really want to become a data mining expert. This is just giving you some of the skills that we've learned in this class and solving some data mining. So the first application that we're going to data mine is an extension of an application we played with back in the JSON chapter. And the idea is it has a queue of locations. These are not pretty locations, meaning they're user typed in locations. They're actually from data from many years ago. It's anonymized data from the students who actually took one of my very first MOOCs, MOOC on Internet History. But it's kind of reduced and anonymized just to play with it. But it's not accurate. We don't have GPS coordinates, but if we use the Google Geodata API with JSON, we can do this. But we we need to avoid rate limiting, so we're going to cache this in a database, meaning we're only going to retrieve data once, and then we're going to use the Google Maps API to visualize this in a browser. And the sample code is right there, and that sample code, geodata.zip, has a README in it and tells you exactly what to do to run this, and it shouldn't be very hard for you to run it and produce a nice visual result. Here's a basic process diagram of what's going to happen. There is a list of the things to retrieve called where.data. It's just a list of locations, but these are not correct. They don't have GPS. They're just as typed into a text field by a user. And geoload is going to start reading this, and it checks to see if it's already in the database. This is a restartable process, as I mentioned. And then it looks to see the first unretrieved data, and then it goes out and does a web service, parses that, then puts it into the database, and then goes to the next one, parses that, puts it in the database. Then this runs for a while, and then maybe it blows up. Then you fix whatever, or you start your computer back up, and runs for a while. So this is a restartable process that in effect is adding stuff to this database. It's an SQLite database, and you can use the SQLite browser to look at this if you like, stuff we did in the database chapter. So you can run that, you can see what you got, run it some more, see what you got, debug it by using the SQLite browser. And then at some point you've got all of your data, and you've got a couple of things. We've got this application called geodump.py that sort of reads through all of this data and then prints some information out, nice summary information. It's real common to want to do this, to get some summary information just for sanity checking, so you don't have to use SQLite browser. But this also writes out a little JavaScript file called where.js, which then combined with where.html and the Google APIs, this uses JavaScript to put all these little pins on based on whatever data is in this database. And so that's our first kind of end-to-end spider process visualize. First thing. So up next, we're going to show how we can use this to build a very simple search engine and then run the PageRank algorithm. Hello everybody, welcome to Python for Everybody. This is another worked code example. You can download the sample code zip file if you want to follow along. And the code that we're working on today is what I call the geodata code, and that is code that is going to pull some locations from this file. We're simulating or using the Google Places API to look places up, and so we can visualize them on a map. And so this is the basic picture. If we take a look at this where.data file, it's just a flat file that has a list of organizations, and this actually was pulled from one of my MOOC surveys. We just let people type in where they went to school, and this is just a sample of them. So this data is read in by this program geoload.py. And if you recall, this Google Geodata has rate limits. It also has API keys, which we'll talk about in a bit too. And so the idea is this is a restartable spider-like process. And so we want to be able to run this and have it blow up and run it and start it and not lose what we've got, right? And so this is unlike some of those. So we're not now using a database as well as an API, but in order to work around the rate limits of this API, we're going to use the database with a restartable process. And then we'll make some sense of this, and then we'll visualize this. But in the short term, let's start with geoload.py code. Geoload.py, take a look here. So a lot of this hopefully by now is somewhat familiar to you. URL lib, JSON, SQLite. And so I mentioned that the Google APIs, these used to be free and did not require an API key, but increasingly they're making you do API keys for especially new ones. And so what happens, you can go to your Google Places, go to Google APIs and get an API key, and you can put it in here. It'll be this big long thing that looks like that. And then if you have an API key, you can use the Places API. And I've got a copy of a subset, not all of it, a subset of it here at this URL. As a matter of fact, you can just go to this URL in a browser, and it will tell you a list of the data that it knows about. Okay, and I made it so that does the same basic protocol with the address. Address equals as the Google Places API. So this will just change how we retrieve the data. Either retrieve it from my server. Nice thing about my server, it's got no rate limit. It's really fast, and you're not fighting with Google all the time. And it means that perhaps if you're in a country that Google is not well supported, you can use my API. I mean, that's really strange that somehow my API is more reliable and available than the Google one, but it's true. So we're going to make a database. We're going to do a create table if not exists, and we'll have some address, and we're really just caching the geographical data. We're going to cache the JSON. One of the things we do when we build these processes is we tend to simplify these things and not do all the calculation and parsing of the JSON. Just load it and get it in, and load it and get it in, and fill the data up in this database. And so that's what we're going to do. Because Python doesn't ship with any legitimate certificates, we have to sort of ignore certificate errors. We're going to open the file, and we're going to loop through it and pull out the address from the file, and we are going to select from the geodata where that address is the address. Let's move this in a bit. And so we're going to do a select and pull out that address. And the idea is if it's already in the database, we don't want to do it. So we do a fetch one and pull out that first thing, which is that will be the JSON right there. If we get that, we'll continue up. Otherwise, we'll keep going. Pass just means don't blow up. So we accept and we just do a pass. That's like a no op. And we're going to make a dictionary because that's what we do for the key value pairs. Everything you've seen so far, I've used constants here, but because we may or may not have an API key, query equals, and then that's the address, and then the key equals, and then the API key. If you recall, URL encode adds the pluses and question marks and all that nice stuff. We're going to retrieve it. We're going to read it and decode it, print out how much data we've got, and add a count. And then we're going to try to parse that JSON data and print it if something goes wrong. And as we've seen, at this top level of this JSON data from this geocoding API is an object, which we'll see a little bit of it in a bit. And it has a status field in it. And the status is okay if things went well. So if the status is not there, that means our JavaScript is not well formed or not how we expect it. If the status is not okay, or not equal to 0 results, then print out failure to retrieve and then quit. And then we're simply going to insert this new data that we just put in, and then we're going to commit it. And every 10th one, this is count mod 10, we're going to pause for 5 seconds, and we can hit Control C here, and then we're going to do the geodump. Okay, so let's just run this. Geodata Python. So let's do an ls. So we don't have, we do have, let's get rid of from a previous test, geodata.sqlite. So we'll start with a fresh set of data and run python geoload.py. Of course, I'm always forever making the mistake of forgetting Python 3. So you can see that it's running and it's adding the query, and in this case I don't have the API key, and it's putting the pluses in, and that's this part here with all the pluses. That's the URL encode. And you notice it's pausing a bit. Now, it depends on how fast your net connection. This may or may not go so fast, but this is not that much data, so it's like only 2,000, 3,000 characters. And so it's working and talking to my server. And the interesting thing here is I can blow this up. I'm going to hit Control C. In Windows, you'd hit Control. In Linux, you'd hit Control C, and in Windows, I think you'd hit Control Z, depending on what shell you're working in. But I'm going to hit Control C, and you see I sort of blew it up, right? And causes a traceback, a keyboard interrupt traceback. If I do an ls-l, you can see that now this geodata is there. Now, in the name of restarting, I will restart this, and you will see that it checks and skips, and so it runs this code here where it's right here. It grabs it and finds it in the database. So you'll see it say found in the database really quick, chop, 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 and go really fast, and then it'll go back to catching up where it left off. And so all those up there, they did not actually retrieve it because it knew about those things. And so now it's catching up and doing some more and doing some more and doing some more. And then I'll hit Control C. It has a little counter in here that basically, if it hits 200, it stops and you have to restart it. You could obviously change this code. You could make it so it didn't sleep. It doesn't hurt to sleep for like a second after every 100 or so if you want. You could change that code. And now let's just hit Control C and blow it up, ls-l. And there is another bit of code, and this code, it's always good to write these really simple things. And so we're going to import SQLite and JSON. We're going to connect ourselves up. We're going to open, except this is a UTF-8 because it's a UTF. We're going to open this with UTF-8, and we're going to read through. And in this case, we are going to decode. We did select star from locations, and if you recall, locations has a location and a geodata. And so the sub-0 will be the location and the sub-1 will be the geodata. And we're going to parse it, convert it to a string, and then parse it. If something goes wrong with the JSON, we'll just keep skipping it. We'll check to see if we have the status in our JSON. Let me run the SQLite browser here. File open database. Let's take a look at what's in this database. Oh, where are we? Code 3, geodata SQLite. So this is the data we've got. So if you make this a little bigger, if I can I make that bigger? Yeah, it's not going to show us much. So you can see that these are the addresses in the geodata. That's just the JSON. So that's the JSON that we got, and it retrieves it. And so this is a really simple database. This just a sort of spidering process, run. But now we're going to run the geodump code, which is going to read this and dump this stuff out and print where.js. So it's going to actually parse this stuff. And that's code we've seen before. And so we're actually reading it. And this line goes into the results. Results is an array. So if we go into results is an array. We're going to go grab the 0th item in that array. And then we're going to go find geometry, and then location, and then lat and long for the latitude and longitude. And then we're also going to take the actual address out of the formatted address right here. So in this bit of code, we're actually parsing the JSON, and we're going to clean things up, get rid of some single quotes. This kind of data cleaning is just stuff after you play with it for a while, you realize, oh, my data is ugly or does this. I'm going to print it out, and then I'm going to write this out, and I'm going to write it into a JavaScript file. And so the JavaScript file is this where.js, and this, I'll show you what it looks like. It's going to be overwritten. This is the one that came out of the zip file. It'll have the latitude, the longitude, and we're going to use JavaScript to read this in this where.html file. It's going to actually read this right there and pull that data in, and that's how we're going to visualize. I'm not going to go into great detail on how the visualization happens, but that's what's happening, and so we're going to write that. So we're going to actually write this to a file. So let's go ahead and run this code and say Python 3 geodump. Okay, so it wrote 120 records to where.js. So if we look at where.js, this is now the new data that I just downloaded moments ago. And it says open where.html in a browser. Now this you'll need the Google Maps API, and you might not be able to see this depending on where you're at, but here you go with Google Maps locations, and I think if you hover over this, you can see, and you see the UTF, why we there in that particular thing, why we had to use the UTF-8 when we wrote the file, so that we didn't end up with trouble writing the file out. And so there you go. And so that is a simple visualization, and just a simple visualization. It wrote this where.js. If you are smart with HTML and JavaScript, you can look at this where.html file. It's really just reading through a bunch of data and putting the points. That's all there is. But I'm not going to go through that. So, at least not in this. And so I hope that this was useful to you. And thanks for watching.